Welcome back. In the last video, we wrote some code to download a series of helper functions from our helperfunctions.py. And later on, you'll see why this is quite standard practice as you write more and more code, is to write some code, store them somewhere, such as a Python script like this. And then instead of us rewriting everything that we have in helper functions, we just import them and then use them later on. This is similar to what we've been doing with PyTorch. PyTorch is essentially just a collection of Python scripts that we're using to build neural networks. Well, there's a lot more than what we've just done. I mean, we've got one here, but PyTorch is a collection of probably hundreds of different Python scripts. But that's beside the point. We're trying to train a model here to separate blue and red dots. But our current model is only drawing straight lines. And I got you to have a think about whether our straight line model, our linear model, could ever separate this data. Maybe it could. And I issued the challenge to see if it could if you trained for 1,000 epochs. So, did it improve at anything? Is the accuracy any higher? Well, speaking of training for more epochs, we're up to section number 5, improving a model. This is from a model perspective. So now let's discuss some ways if you were getting results after you train a machine learning model or a deep learning model, whatever kind of model you're working with, and you weren't happy with those results. So how could you go about improving them? So this is going to be a little bit of an overview of what we're going to get into. So one way is to add more layers. So give the model more chances to learn about patterns in the data. Why would that help? Because if our model currently has 2 layers, model 0 dot state dict, well, we've got however many numbers here, 20 or so. So this is 0th layer, this is the first layer. If we had 10 of these, well, we'd have 10 times the amount of parameters to try and learn the patterns in this data, a representation of this data. Another way is to add more hidden units. So what I mean by that is we created this model here, and each of these layers has 5 hidden units. The first one outputs, out features equals 5, and this one takes in features equals 5. So we could go from 5 hidden units to 10 hidden units. The same principle as above applies here, is that the more parameters our model has to represent our data, the potentially, now I say potentially here because some of these things might not necessarily work. So our data set is quite simple. So maybe if we added too many layers, our model's trying to learn things that are too complex. It's trying to adjust too many numbers for the data set that we have. The same thing for more hidden units. What other options do we have? Well, we could fit for longer, give the model more of a chance to learn because every epoch is one pass through the data. So maybe 100 times looking at this data set wasn't enough. So maybe you could fit for 1,000 times, which was the challenge. Then there's changing the activation functions, which we're using sigmoid at the moment, which is generally the activation function you use for a binary classification problem. But there are also activation functions you can put within your model. There's a little hint. We'll get to that later. Then there's change the learning rate. So the learning rate is the amount the optimizer will adjust these every epoch. And if it's too small, our model might not learn anything because it's taking forever to change these numbers. But if also on the other side of things, if the learning rate is too high, these updates might be too large and our model might just explode. There's an actual problem in machine learning called exploding gradient problem, where the numbers just get too large. On the other side, there's also a vanishing gradients problem, where the gradients just go basically to 0 too quickly. And then there's also change the loss function, but I feel like for now, sigmoid and binary cross entropy are pretty good, pretty standard. So we're going to have a look at some options here, add more layers and fit for longer, maybe changing the learning rate, but let's just add a little bit of color to what we've been talking about. Right now, we've fit the model to the data and made a prediction. I'm just going to step through this. Where are we up to? we've done this, we've done this, we've done these two, we've built a training loop, we've fit the model to the data, made a prediction, we've evaluated our model visually, and we're not happy with that. So we're up to number 5. We're going to improve through experimentation. We don't need to use TensorBoard just yet. We're going to talk about this as a high level. TensorBoard is a tool or a utility from PyTorch, which helps you to monitor experiments. We'll see that later on. And then we'll get to this. We won't save our model until we've got one that we're happy with. And so, if we look at what we've just talked about, improving a model from a model's perspective, let's talk about the things we've talked about with some color this time. So, say we've got a model here. This isn't the exact model that we're working with, but it's similar structure. We've got 1, 2, 3, 4 layers. We've got a loss function, BCE with logits loss. We've got an optimizer, stochastic gradient descent. And if we did write some training code, this is 10 epochs. And then the testing code here, I've just cut it out because it wouldn't fit on the slide. Then if we wanted to go to a larger model, let's add some color here so we can highlight what's happening. Adding layers. Okay, so this one's got 1, 2, 3, 4, 5, 6 layers. And we've got another color here, which is, I'd say this is like a little bit of a greeny blue. Increase the number of hidden units. Okay, so the hidden units are these features here. We've gone from 100 to 128 to 128. Remember, the out features of a previous layer have to line up with the in features of a next layer. And then we've gone to 256. Wow! So remember how I said multiples of 8 are pretty good generally in deep learning? Well, this is where these numbers come from. And then what else do we have? Change/add activation functions. We haven't seen this before, nn.relu. If you want to jump ahead and have a look at what nn.relu is, how would you find out about it? Well, I'd just Google nn.relu, but we're going to have a look at what this is later on. We can see here that this one's got 1, but this larger model has some relus scattered between the linear layers. Maybe that's a hint. If we combine a linear layer with a relu, what's a relu layer? I'm not going to spoil this, we're going to find out later on. Change the optimization function. Oh, okay. So we've got SGD. Do you recall how I said Atom is another popular one that works fairly well across a lot of problems as well? So Atom might be a better option for us here. The learning rate as well. So maybe this learning rate was a little too high, and so we've divided it by 10. And then finally, fitting for longer. So instead of 10 epochs, we've gone to 100. So how about we try to implement some of these with our own model to see if it improves what we've got going on here. Because frankly, like, this isn't satisfactory. We're trying to build a neural network here. Neural networks are supposed to be these models that can learn almost anything, and we can't even separate some blue dots from some red dots. So in the next video, how about we run through writing some code to do some of these steps here? In fact, if you want to try yourself, I'd highly encourage that. So I'd start with trying to add some more layers and add some more hidden units and fitting for longer. You can keep all of the other settings the same for now. But I'll see you in the next video. Welcome back. In the last video, we discussed some options to improve our model from a model perspective. And namely, we're trying to improve it so that the predictions are better, so that the patterns it learns better represent the data, so we can separate blue dots from red dots. And you might be wondering why we said from a model perspective here. So let me just write these down. These options are all from a model's perspective because they deal directly with the model rather than the data. So there's another way to improve a model's results is if the model was sound already. In machine learning and deep learning, you may be aware that generally if you have more data samples, the model learns or gets better results because it has more opportunity to learn. There's a few other ways to improve a model from a data perspective, but we're going to focus on improving a model from a model's perspective. So, and because these options are all values we as machine learning engineers and data scientists can change, they are referred to as hyperparameters. So a little bit of an important distinction here. Parameters are the numbers within a model. The parameters here, like these values, the weights and biases, are Parameters are the values a model updates by itself. Hyperparameters are what we as machine learning engineers and data scientists, such as adding more layers, more hidden units, fitting for longer number of epochs, activation functions, learning rate, loss functions, are hyperparameters because they're values that we can change. So let's change some of the hyperparameters of our model. So we'll create circle model v1. We're going to import from nn.module as well. We could write this model using nn.sequential, but we're going to subclass nn.module for practice. Why would we use nn.sequential? Well, because as you'll see, our model is not too complicated, but we subclass nn.module. In fact, nn.sequential, so if we write here, nn.sequential, is also a version of nn.module. But we subclass nn.module here for practice, and for later on, if we wanted to, or if you wanted to make more complex models, you're going to see a subclass of nn.module a lot in the wild. So the first change we're going to update is the number of hidden units. So out features, I might write this down before we do it. Let's try and improve our model by adding more hidden units. So this will go from 5 and we'll increase it to 10. And we want to increase the number of layers. So we want to go from 2 to 3. We'll add an extra layer and then increase the number of epochs. So we're going to go from 100 to 1,000. Now, we're going to put on our scientist hats for a second. What would be the problem with the way we're running this experiment? If we're doing all three things in one hit, why might that be problematic? Well, because we might not know which one offered the improvement, if there is any improvement, or degradation. So, just to keep in mind going forward, I'm just doing this as an example of how we can change all of these. But generally, when you're doing machine learning experiments, you'd only like to change one value at a time and track the results. So that's called experiment tracking in machine learning. We're going to have a look at experiment tracking a little later on in the course, but just keep that in mind. A scientist likes to change one variable of what's going on so that they can control what's happening. But we're going to create this next layer here, layer 2, and of course it takes the same number of out features as in features as the previous layer. This is 2 because why? Our X train has, let's look at just the first 5 samples, has 2 features. So now we're going to create self layer 3, which equals nn.linear. The in features here is going to be 10. Why? Because the layer above has out features equals 10. So what we've changed here so far is we've got hidden units previously in V0 of this model was 5. And now we've got a third layer, which previously before was 2. So these are 2 of our main changes here. And out features equals 1 because, why? Let's have a look at, speaking of why, our y is just one number. So remember, the shapes, the input and output shapes of a model is one of the most important things in deep learning. We're going to see different values for these shapes later on, but because we're working with this data set, we're focused on 2 in features and 1 out feature. So now that we've got our layers prepared, what's next? Well, we have to override the forward method because every subclass of nn.module has to implement a forward method. So what are we going to do here? Well, let me just show you one option. We could go Z, which would be Z for logits. Logits is actually represented by a Z, fun fact, but you could actually put any variable here. So this could be x1, or you could reset x if you wanted to. I just look putting a different one because it's a little less confusing for me. And then we could go update Z by going self layer 2, and then because Z above is the output of layer 1, it now goes into here. And then if we go Z again equals self layer 3, what's this going to take? It's going to take Z from above. So this is saying, hey, give me X, put it through layer 1, assign it to Z, and then create a new variable Z or override Z with self layer 2, with Z from before as the input. And then we've got Z again, the output of layer 2 as the input for layer 3. And then we could return Z. So that's just passing our data through each one of these layers here. But a way that you can leverage speedups in PyTorch is to call them all at once. So layer 3, and we're going to put self dot layer 2. And this is generally how I'm going to write them. But it also, behind the scenes, because it's performing all the operations at once, you leverage whatever speedups you can get. Oh, this should be layer 1. So it goes in order here. So what's happening? Well, it's computing the inside of the brackets first. So layer 1, X is going through layer 1. And then the output of X into layer 1 is going into layer 2. And then the same again for layer 3. So this way of writing operations leverages speedups where possible behind the scenes. And so we've done our forward method there. We're just passing our data through layers with extra hidden units and an extra layer overall. So now let's create an instance of circle model v1, which we're going to set to model 1, and we're going to write circle model v1, and we're going to send it to the target device because we like writing device agnostic code. And then we're going to check out model 1. So let's have a look at what's going on there. Beautiful. So now we have a 3-layered model with more hidden units. So I wonder if we trained this model for longer, are we going to get improvements here? So my challenge to you is we've already done these steps before. We're going to do them over the next couple of videos for completeness. But we need to what? Create a loss function. So I'll give you a hint. It's very similar to the one we've already used. And we need to create an optimizer. And then once we've done that, we need to write a training and evaluation loop for model 1. So give that a shot. Otherwise, I'll see you in the next video. We'll do this all together. Welcome back. In the last video, we subclassed nn.module to create circle model v1, which is an upgrade on circle model v0 in the fact that we added more hidden units, so from 5 to 10, and we added a whole extra layer. And we've got an instance of it ready to go. So we're up to, in the workflow, we've got our data. Well, we haven't changed the data, so we've built our new model. We now need to pick a loss function. And I hinted at before that we're going to use the same loss function as before, the same optimizer. You might have already done all of these steps, so you may know whether this model works on our data set or not. But that's what we're going to work towards finding out in this video. So we've built our new model. Now let's pick a loss function and an optimizer. We could almost do all of this with our eyes closed now. Build a training loop, fit the model to the data, make a prediction, and evaluate the model. We'll come back here, and let's set up a loss function. And by the way, if you're wondering, like, why would adding more features here, we've kind of hinted at this before, and why would an extra layer improve our model? Well, again, it's back to the fact that if we add more neurons, if we add more hidden units, and if we add more layers, it just gives our model more numbers to adjust. So look at what's going on here. Layer 1, layer 2. Look how many more we have compared to model 0.stateDict. We have all of these. This is model 0, and we just upgraded it. Look how many more we have from just adding an extra layer and more hidden units. So now we have our optimizer can change these values to hopefully create a better representation of the data we're trying to fit. So we just have more opportunity to learn patterns in our target data set. So that's the theory behind it. So let's get rid of these. Let's create a loss function. What are we going to use? Well, we're going to use nn.bce with logits loss. And our optimizer is going to be what? We're going to keep that as the same as before, torch.optim.sgd. But we have to be aware that because we're using a new model, we have to pass in params of model 1. These are the parameters we want to optimize. And the LR is going to be 0.1. Is that the same LR we used before, learning rate 0.1? Oh, potentially our learning rate may be too big. 0.1. Where do we create our optimizer? See, we've written a lot of code here. Optimizer, there we go, 0.1, that's all right. So we'll keep it at 0.1 just to keep as many things the same as possible. So we're going to set up torch.manualseed 42 to make training as reproducible as possible. Torch.cuda.manualseed 42. Now, as I said before, don't worry too much if your numbers aren't exactly the same as mine. The direction is more important, whether it's good or bad direction. So now let's set up epochs. We want to train for longer this time as well. So 1,000 epochs. This is one of our 3 improvements that we're trying to do. Adding more hidden units, increase the number of layers, and increase the number of epochs. So we're going to give our model 1,000 looks at the data to try and improve its patterns. So put data on the target device. We want to write device agnostic code. And yes, we've already done this, but we're going to write it out again for practice, because even though we could functionize a lot of this, it's good while we're in still the foundation stages to practice what's going on here, because I want you to be able to do this with your eyes closed before we start to functionize it. So put the training data and the testing data to the target device, whatever it is, CPU or GPU. And then we're going to, well, what's our song? For an epoch in a range. Let's loop through the epochs. We're going to start off with training. What do we do for training? Well, we set model 1 to train. And then what's our first step? Well, we have to forward pass. What's our outputs of the model? Well, the raw outputs of a model are logits. So model 1, we're going to pass it the training data. And we're going to squeeze it so that we get rid of an extra 1 dimension. If you don't believe me that we would like to get rid of that 1 dimension, try running the code without that dot squeeze. And ypred equals torch.round and torch.sigmoid. Why? We're calling sigmoid on our logits to go from logits to prediction probabilities to prediction labels. And then what do we do next? Well, we calculate the loss / accuracy to here. And remember, accuracy is optional, but loss is not optional. So we're going to pass in here, our loss function is going to take in, I wonder if it'll work with just straight up ypred. I don't think it will, because we need logits in here. Ylogits and ytrain. Because why? Oh, Google Colab correcting the wrong thing. We have ylogits because we're using BCE with logits loss here. So let's keep pushing forward. We want our accuracy now, which is our accuracy function. And we're going to pass in the order here, which is the reverse of above. A little confusing, but I've kept the evaluation function in the same order as scikit-learn. Ypred equals ypred. 3, we're going to zero the gradients of the optimizer. Optimizer 0 grad. And you might notice that we've started to pick up the pace a little. That is perfectly fine. If I'm typing too fast, you can always slow down the video, or you could just watch what we're doing and then code it out yourself afterwards. The code resources will always be available. We're going to take the loss backward and perform back propagation. The only reason we're going faster is because we've covered these steps. So anything that we sort of spend time here, we've covered in a previous video. Optimizer step. And this is where the adjustments to all of our model's parameters are going to take place to hopefully create a better representation of the data. And then we've got testing. What's the first step that we do in testing? Well, we call model1.eval to put it in evaluation mode. And because we're making predictions, we're going to turn on Torch inference mode. Predictions, I call them predictions. Some other places call it inference. Remember, machine learning has a lot of different names for the same thing. Forward pass. So we're going to create the test logits here equals model1 x test, and we're going to squeeze them because we don't want the extra 1 dimension. Just going to add some code cells here so that we have more space, and I'm typing in the middle of the screen. Then I'm going to put in test pred here. How do we get from logits to predictions? Well, we go torch.round, and then we go torch.sigmoid. Why sigmoid? Because we're working with a binary classification problem, and to convert logits from a binary classification problem to prediction probabilities, we use the sigmoid activation function, and then we're going to calculate the loss. So how wrong is our model on the test data? So test lost equals loss function. We're going to pass it in the test logits, and then we're going to pass it in y test for the ideal labels, and then we're going to also calculate test accuracy. And test accuracy is going to take in y true equals y test, so the test labels, and y pred equals test pred, so the test predictions. Test predictions here. And our final step is to print out what's happening. So print out what's happening. Oh, every tutorial needs a song. If I could, I'd teach everything with song. Song and dance. So because we're training for 1,000 epochs, how about every 100 epochs we print out something? So print f string, and we're going to write epoch in here so we know what epoch our model's on, and then we're going to print out the loss. Of course, this is going to be the training loss because the test loss has test at the front of it, and then the accuracy here. Now, of course, this is going to be the training accuracy. We go here, and then we're going to pipe, and we're going to print out the test loss, and we want the test loss here. We're going to take this to 5 decimal places. Again, when we see the printouts of the different values, do not worry too much about the exact numbers on my screen appearing on your screen, because that is inherent to the randomness of machine learning. So have we got, the direction is more important. Have we got, we need a percentage sign here because that's going to be a bit more complete for accuracy. Have we got any errors here? I don't know. We've just all coded this freehand, right? There's a lot of code going on here. So we're about to train our next model, which is the biggest model we've built so far in this course. 3 layers, 10 hidden units on each layer. Let's see what we've got. 3, 2, 1, run. Oh, what? What? 1,000 epochs, an extra hidden layer, more hidden units, and our model is still basically a coin toss. 50%. Now, this can't be for real. Let's plot the decision boundary. Plot the decision boundary. To find out, let's get a bit visual. Plot figure. Actually, to prevent us from writing out all of the plot code, let's just go up here and we'll copy this. Now, you know I'm not the biggest fan of copying code, but for this case, we've already written it, so there's nothing really new here to cover. And we're going to just change this from model 0 to model 1 because why? It's our new model that we just trained. And so behind the scenes, plot decision boundary is going to make predictions with the target model on the target data set and put it into a nice visual representation for us. Oh, I said nice visual representation. What does this look like? We've just got a coin toss on our data set. Our model is just, again, it's trying to draw a straight line to separate circular data. Now, why is this? Our model is based on linear. Is our data non-linear? Maybe I've revealed a few of my tricks. I've done a couple of reveals over the past few videos, but this is still quite annoying, and it can be fairly annoying when you're training models and they're not working. So how about we verify that this model can learn anything? Because right now it's just basically guessing for our data set. So this model looks a lot like the model we built in section 01. Let's go back to this. This is the Learn PyTorch.io book. PyTorch Workflow Fundamentals. Where did we create a model? Model Building Essentials. Where did we build a model? Linear regression model. Yeah, here. nn.linear. But we built this model down here. So all we've changed from 01 to here is we've added a couple of layers. The forward computation is quite similar. If this model can learn something on a straight line, can this model learn something on a straight line? So that's my challenge to you is grab the data set that we created in this previous notebook. So data, you could just reproduce this exact data set. and see if you can write some code to fit the model that we built here, this one here, on the data set that we created in here. Because I want to verify that this model can learn anything. Because right now it seems like it's not learning anything at all. And that's quite frustrating. So give that a shot, and I'll see you in the next video. Welcome back. In the past few videos, we've tried to build a model to separate the blue from red dots, yet our previous efforts have proven futile. But don't worry, we're going to get there. I promise you we're going to get there. And I may have a little bit of inside information here, but we're going to build a model to separate these blue dots from red dots, a fundamental classification model. And we tried a few things in the last couple of videos, such as training for longer, so more epochs. We added another layer. We increased the hidden units because we learned of a few methods to improve a model from a model perspective, such as upgrading the hyperparameters, such as number of layers, more hidden units, fitting for longer, changing the activation functions, changing the learning rate. We haven't quite done that one yet, and changing the loss function. One way that I like to troubleshoot problems is I'm going to put a subheading here, 5.1. We're going to preparing data to see if our model can fit a straight line. So one way to troubleshoot, this is my trick for troubleshooting problems, especially neural networks, but just machine learning in general. To troubleshoot a larger problem is to test out a smaller problem. And so why is this? Well, because we know that we had something working in a previous section. So 01 PyTorch workflow fundamentals, we built a model here that worked. And if we go right down, we know that this linear model can fit a straight line. So we're going to replicate a data set to fit a straight line to see if the model that we're building here can learn anything at all, because right now it seems like it can't. It's just tossing a coin to split between our data here, which is not ideal. So let's make some data. But yeah, this is let's create a smaller problem, one that we know that works, and then add more complexity to try and solve our larger problem. So create some data. This is going to be the same as Notebook 01. And I'm going to set up weight equals 0.7, bias equals 0.3. We're going to move quite quickly through this because we've seen this in module 1. But the overall takeaway from this is we're going to see if our model works on any kind of problem at all, or do we have something fundamentally wrong. Create data. We're going to call it X regression because it's a straight line and we want it to predict a number rather than a class. So you might be thinking, oh, we might have to change a few things of our model architecture. Well, we'll see that in a second. Dot unsqueeze, and we're going to go on the first dimension here, or dim equals 1. And Y regression, we're going to use the linear regression formula as well. Weight times X regression that is, because we're working with a new data set here, plus the bias. So this is linear regression formula without epsilon. So it's a simplified version of linear regression, but the same formula that we've seen in a previous section. So now let's check the data. Nothing we really haven't covered here, but we're going to do a sanity check on it to make sure that what we're dealing with is not just a load of garbage. Because it's all about the data in machine learning. I can't stress to you enough. That's the Data Explorer's motto, is to visualize, visualize, visualize. Oh, what did we get wrong here? Unsqueeze, did you notice that typo? Why didn't you say something? I'm kidding. There we go. Okay, so we've got 100 samples of X. We've got a different step size here, but that's all right. Let's have a little bit of fun with this. And we've got one X value per Y value. This is a very similar data set to what we used before. Now, what do we do once we have a data set? Well, if we haven't already got training and test splits, we better make them. So create train and test splits. And then we're going to go train split. We're going to use 80% equals int 0.8 times the length of, or we could just put 100 in there, but we're going to be specific here. And then we're going to go X train regression, Y train regression equals, what do these equal? Well, we're going to go on X regression, and we're going to index up to the train split on the X, and then for the Y regression, we're going to index up to the train split. Wonderful. And then we can do the same on the test, or creating the test data. Nothing really new here that we need to discuss. We're creating training and test sets. What do they do for each of them? Well, the model is going to hopefully learn patterns in the training data set that is able to model the testing data set. And we're going to see that in a second. So if we check the lengths of each, what do we have? Length, X train, regression. We might just check X train, X test, regression. What do we have here? And then we're going to go length, Y train, regression. Long variable names here. Excuse me for that. But we want to keep it separate from our already existing X and Y data. What values do we have here? 80, 20, 80, 20. Beautiful. So 80 training samples to 100 testing samples. That should be enough. Now, because we've got our helper functions file here, and if you don't have this, remember we wrote some code up here before to, where is it? To download it from the course GitHub, and we imported plot predictions from it. Now, if we have a look at helperfunctions.py, it contains the plot predictions function that we created in the last section, section 0.1. There we go. Plot predictions. So we're just running this exact same function here, or we're about to run it. It's going to save us from retyping out all of this. That's the beauty of having a helperfunctions.py file. So if we come down here, let's plot our data to visually inspect it. Right now it's just numbers on a page, and we're not going to plot really any predictions because we don't have any predictions yet, but we'll pass in the train data is equal to X train regression. And then the next one is the train labels, which is equal to Y train regression. And then we have the test data, which is equal to X test regression. And then we have the test labels. Now I think this should be labels too. Yeah, there we go. Y test regression. I might be proven wrong as we try to run this function. Okay, there we go. So we have some training data and we have some testing data. Now, do you think that our model 1, if we have a look, what's model 1, could fit this data? Does it have the right amount of in and out features? We may have to adjust these slightly. So I'd like you to think about that. Do we have to change the input features to our model for this data set? And do we have to change the out features of our model for this data set? We'll find out in the next video. Welcome back. We're currently working through a little side project here, but really the philosophy of what we're doing, we just created a straight line data set because we know that we've built a model in the past, back in section 01, to fit a straight line data set. And why are we doing this? Well, because the model that we've built so far is not fitting or not working on our circular data set here, on our classification data set. And so one way to troubleshoot a larger problem is to test out a smaller problem first. So later on, if you're working with a big machine learning data set, you'd probably start with a smaller portion of that data set first. Likewise, with a larger machine learning model, instead of starting with a huge model, you'll start with a small model. So we're taking a step back here to see if our model's going to learn anything at all on a straight line data set so that we can improve it for a non-straight line data set. And there's another hint. Oh, we're going to cover it in a second, I promise you. But let's see how now we can adjust model 1 to fit a straight line. And I issued you the question at the end of last video. Do we have to adjust the parameters of model 1 in any way, shape or form to fit this straight line data? And you may have realized, or you may not have, that our model 1 is set up for our classification data, which has 2x input features. Whereas this data, if we go X, train regression, how many input features do we have? If we just get the first sample, there's only one value. Or maybe we get the first 10. There's only one value per, let's remind ourselves, this is input and output shapes, one of the most fundamental things in machine learning and deep learning. And trust me, I still get this wrong all the time, so that's why I'm harping on about it. We have one feature per one label, so we have to adjust our model slightly. We have to change the in features to be 1 instead of 2. The out features can stay the same because we want one number to come out. So what we're going to do is code up a little bit different version of model 1. So same architecture as model 1, but using nn.sequential. We're going to do the faster way of coding a model here. Let's create model 2 and nn.sequential. The only thing that's going to change is the number of input features. So this will be the exact same code as model 1, and the only difference, as I said, will be features or in features is 1, and then we'll go out features equals 10. So 10 hidden units in the first layer, and of course the second layer, the number of features here has to line up with the out features of the previous layer. This one's going to output 10 features as well. So we're scaling things up from 1 feature to 10 to try and give our model as much of a chance or as many parameters as possible. Of course, we could make this number quite large. We could make it 1,000 features if we want. But there is an upper bound on these things. And I'm going to let you find those in your experience as a machine learning engineer and a data scientist. But for now, we're keeping it nice and small so we can run as many experiments as possible. Beautiful, look at that. We've created a sequential model. What happens with nn.sequential? Data goes in here, passes through this layer. Then it passes through this layer. Then it passes through this layer. And what happens when it goes through the layer? It triggers the layer's forward method, the internal forward method. In the case of nn.linear, we've seen it. It's got the linear regression formula. So if we go nn.linear, it performs this mathematical operation, the linear transformation. But we've seen that before. Let's keep pushing forward. Let's create a loss and an optimizer. Loss and optimizer. We're going to work through our workflow. So loss function, we have to adjust this slightly. We're going to use the L1 loss because why? We're dealing with a regression problem here rather than a classification problem. And our optimizer, what can we use for our optimizer? How about we bring in just the exact same optimizer, SGD, that we've been using for our classification data. So model 2.params or parameters. I always get a little bit confused. And we'll give it an LR of 0.1 because that's what we've been using so far. This is the params here. So we want our optimizer to optimize our model 2 parameters here with a learning rate of 0.1. The learning rate is what? The amount each parameter will be, or the multiplier that will be applied to each parameter each epoch. So now, let's train the model. Do you think we could do that in this video? I think we can. So we might just train it on the training data set, and then we can evaluate it on the test data set separately. So we'll set up both manual seeds, CUDA, and because we've set our model to the device up here, so it should be on the GPU or whatever device you have active. So set the number of epochs. How many epochs should we set? Well, we set 1,000 before, so we'll keep it at that. Epochs equals 1,000. And now we're getting really good at this sort of stuff here. Let's put our data, put the data on the target device. And I know we've done a lot of the similar steps before, but there's a reason for that. I've kept all these in here because I'd like you to, by the end of this course, is to sort of know all of this stuff off by heart. And even if you don't know it all off by heart, because trust me, I don't, you know where to look. So X-train regression, we're going to send this to device. And then we're going to go Y-train regression. Just a reminder or something to get you to think while we're writing this code. What would happen if we didn't put our data on the same device as a model? We've seen that error come up before, but what happens? Well, I've just kind of given it away, haven't you, Daniel? Wow, that was a great question. Our code will error. Oh, well, don't worry. There's plenty of questions I've been giving you that I haven't given the answer to yet. device, beautiful. We've got a device agnostic code for the model and for the data. And now let's loop through epochs. So train, we're gonna for epoch in range epochs, for an epoch in a range, do the forward pass, calculate the loss. So ypred equals model2, this is the forward pass, xtrain, regression, it's all going to work out hunky-dory because our model and our data are on the same device. Loss equals what? We're going to bring in our loss function. We're going to compare the predictions to ytrain regression to the y labels. What do we do next? Optimizer 0 grad, optimizer.0 grad. We're doing all of this without comments. Look at us go. Loss backward, and what's next? Optimizer step, step, step. And of course, we could do some testing here. Testing, we'll go model2.eval, and then we'll go with torch.inference mode. We'll do the forward pass, we'll create the test predictions equals model2.xtest regression. And then we'll go the test loss equals loss fn on the test predictions and versus the y test labels. Beautiful. Look at that. We've just done an optimization loop, something we spent a whole hour on before, maybe even longer, in about 10 lines of code. And of course, we could shorten this by making these a function. But we're going to see that later on. I'd rather us give a little bit of practice while this is still a bit fresh. Print out what's happening. Let's print out what's happening. What should we do? So because we're training for 1,000 epochs, I like the idea of printing out something every 100 epochs. That should be about enough of a step. Epoch, what do we got? We'll put in the epoch here with the F string, and then we'll code the loss, which will be loss, and maybe we'll get the first 5 of those, 5 decimal places that is. We don't have an accuracy, do we? Because we're working with regression. And we'll get the test loss out here, and that's going to be 0.5f as well. Beautiful. Have we got any mistakes? I don't think we do. We didn't even run this code cell before. We'll just run these 3 again, see if we got... Look at that! Oh my goodness, is our loss is going down. So that means our model must be learning something. Now, what if we adjusted the learning rate here? I think if we went 0.01 or something, will that do anything? Oh yes, look how low our loss gets on the test data set, but let's confirm that. We've got to make some predictions. Or maybe we should do that in the next video. Yeah, this one's getting too long, but how good's that? We created a straight line data set, and we've created a model to fit it. We set up a loss and an optimizer already, and we put the data on the target device. We trained and we tested, so our model must be learning something, but I'd like you to give a shot at confirming that by using our plot predictions function. So make some predictions with our trained model. Don't forget to turn on inference mode, and we should see some red dots here, fairly close to the green dots on the next plot. Give that a shot, and I'll see you in the next video. Welcome back. In the last video, we did something very exciting. We solved a smaller problem that's giving us a hint towards our larger problem. So we know that the model that we've previously been building, Model 2, has the capacity to learn something. Now, how did we know that? Well, it's because we created this straight line data set. We replicated the architecture that we used for Model 1. Recall that Model 1 didn't work very well on our classification data, but with a little bit of an adjustment, such as changing the number of in features, and not too much different training code except for a different loss function because, well, we use MAE loss with regression data. And we changed the learning rate slightly because we found that maybe our model could learn a bit better. And again, I'd encourage you to play around with different values of the learning rate. In fact, anything that we've changed, try and change it yourself and just see what happens. That's one of the best ways to learn what goes on with machine learning models. But we trained for the same number of epochs. We set up device agnostic code. We did a training and testing loop. Look how good this looks. Oh my goodness, well done. And our loss went down. So, What does that tell us? Well, it tells us that Model 2, or the specific architecture, has some capacity to learn something. So we must be missing something. And we're going to get to that in a minute, I promise you. But we're just going to confirm that our model has learned something and it's not just numbers on a page going down by getting visual. So turn on, we're going to make some predictions and plot them. And you may have already done this because I issued that challenge at the end of the last video. So turn on evaluation mode. Let's go model2.eval, and let's make predictions, which are also known as inference. And we're going to go with torch.inference mode, with torch.inference mode. Make some predictions. We're going to save them as y_preds, and we're going to use model 2, and we're going to pass it through x_test regression. This should all work because we've set up device agnostic code, plot data, and predictions. To do this, we can of course use our plot predictions function that we imported via our helper functions.py function. The code for that is just a few cells above if you'd like to check that out. But let's set up the train data here. Train data parameter, which is xtrain regression. And my goodness, Google Colab, I'm already typing fast enough. You don't have to slow me down by giving me the wrong autocorrects. Train label equals ytrain regression. And then we're going to pass in our test data equals x_test regression. And then we're going to pass in test labels, which is y_test regression. We've got too many variables going on here. My goodness gracious. We could have done better with naming, but this will do for now. Is y_preds. And then if we plot this, what does it look like? Oh no! We got an error. Now, secretly, I kind of knew that that was coming ahead of time. That's the advantage of being the host of this machine learning cooking show. So type error, how do we fix this? Remember how I asked you in one of the last videos what would happen if our data wasn't on the same device as our model? Well, we'd get an error, right? But this is a little bit different as well. We've seen this one before. We've got CUDA device type tensor to numpy. Where is this coming from? Well, because our plot predictions function uses matplotlib, and behind the scenes, matplotlib references numpy, which is another numerical computing library. However, numpy uses a CPU rather than the GPU. So we have to call .cpu, this helpful message is telling us, call tensor.cpu before we use our tensors with numpy. So let's just call .cpu on all of our tensor inputs here and see if this solves our problem. Wonderful, looks like it does. Oh my goodness, look at those red dots, so close. Well, okay, so this just confirms our suspicions. What we kind of already knew is that our model did have some capacity to learn. It's just the data set, when we changed the data set, it worked. So, is it our data that our model can't learn on? Like this circular data? Or is it the model itself? Remember, our model is only comprised of linear functions. What is linear? Linear is a straight line, but is our data made of just straight lines? I think it's got some non-linearities in there. So, the big secret I've been holding back will reveal itself starting from the next video. So if you want a head start on it, I'd go to Torch NN, and if we have a look at the documentation, we've been speaking a lot about linear functions. What are these? Non-linear activations. And I'll give you another spoiler. We've actually seen one of these non-linear activations throughout this notebook. So go and check that out, see what you can infer from that, and I'll see you in the next video. Let's get started with non-linearities. Welcome back. In the last video, we saw that the model that we've been building has some potential to learn. I mean, look at these predictions. You could get a little bit better, of course, get the red dots on top of the green dots, but we're just going to leave that. The trend is what we're after. Our model has some capacity to learn, except this is straight line data. And we've been hinting at it a fair bit, is that we're using linear functions. And if we look up linear data, what does it look like? Well, it has quite a straight line. If we go linear, and just search linear, what does this give us? Linear means straight. There we go, straight. And then what happens if we search for non-linear? I kind of hinted at this as well. Non-linear. Oh, we get some curves. We get curved lines. So linear functions, straight, non-linear functions. Now, this is one of the beautiful things about machine learning. And I'm not sure about you, but when I was in high school, I kind of learned a concept called line of best fit, or y equals mx plus c, or y equals mx plus b, and it looks something like this. And then if you wanted to go over these, you'd use quadratic functions and a whole bunch of other stuff. But one of the most fundamental things about machine learning is that we build neural networks, and deep down, neural networks are just a combination. It could be a large combination of linear functions and non-linear functions. So that's why in torch.nn we have non-linear activations and we have all these other different types of layers. But essentially what they're doing deep down is combining straight lines with, if we go back up to our data, non-straight lines. So of course our model didn't work before because we've only given it the power to use linear lines. We've only given it the power to use straight lines. But our data is what? It's curved. Although it's simple, we need non-linearity to be able to model this data set. And now, let's say we were building a pizza detection model. So let's look up some images of pizza, one of my favorite foods. Images. Pizza, right? So could you model pizza with just straight lines? Now you're thinking, Daniel, you can't be serious. A computer vision model doesn't look for just straight lines in this. And I'd argue that, yes, it does, except we also add some curved lines in here. That's the beauty of machine learning. Could you imagine trying to write the rules of an algorithm to detect that this is a pizza? Maybe you could put in, oh, it's a curve here, and if you see red and... No. Imagine if you're trying to do 100 different foods. Your program would get really large. Instead, we give our machine learning models, if we come down to the model that we created, we give our deep learning models the capacity to use linear and non-linear functions. We haven't seen any non-linear layers just yet. Or maybe we've hinted at some, but that's all right. So we stack these on top of each other, these layers, and then the model figures out what patterns in the data it should use, what lines it should draw to draw patterns through not only pizza, but another food such as sushi. If we wanted to build a food image classification model, it would do this. The principle remains the same. So the question I'm going to pose to you, we'll get out of this, is we'll come down here. We've unlocked the missing piece, or we're about to. We're going to cover it over the next couple of videos. The missing piece of our model. And this is a big one. This is going to follow you out throughout all of machine learning and deep learning. Non-linearity. So the question here is, what patterns could you draw if you were given an infinite amount of straight and non-straight lines? Or in machine learning terms, an infinite amount, but really it is finite. By infinite, in machine learning terms, this is a technicality. It could be 1,000,000 parameters. It could be, as we've got, probably 100 parameters in our model. So just imagine a large amount of straight and non-straight lines, an infinite amount of linear and non-linear functions. You could draw some pretty intricate patterns, couldn't you? And that's what gives machine learning, and especially neural networks, the capacity to not only fit a straight line here, but to separate two different circles, but also to do crazy things like drive a self-driving car, or at least power the vision system of a self-driving car. Of course, after that, you need some programming to plan what to actually do with what you see in an image. But we're getting ahead of ourselves here. Let's now start diving into non-linearity. And the whole idea here is combining the power of linear and non-linear functions. Straight lines and non-straight lines. Our classification data is not comprised of just straight lines, it's circles. So we need non-linearity here. So recreating non-linear data, red and blue circles. We don't need to recreate this, but we're going to do it anyway for completeness. So let's get a little bit of a practice. Make and plot data. This is so that you can practice the use of non-linearity on your own. Matplotlib.pyplot as PLT. We're going to go a bit faster here because we've covered this code above. So import make circles. We're just going to recreate the exact same circle data set that we've created above. number of samples, we'll create 1,000, and we're going to create x and y equals what? Make circles, pass it in number of samples, beautiful. Colab, please, I wonder if I can turn off autocorrect on Colab. I'm happy to just see all of my errors in the flesh. See, look at that. I don't want that. I want noise like that. Maybe I'll do that in the next video. We're not going to spend time here looking around how to do it. We can work that out on the fly later. For now, I'm too excited to share with you the power of non-linearity. So here, x, we're just going to plot what's going on. We've got two x features, and we're going to color it with the flavor of y, because we're doing a binary classification. And we're going to use one of my favorite CMaps, which is color map, and we're going to go plt.cm for CMap and red, blue. What do we get? Okay, red circle, blue circle. Hey, is that the same color as what's above? I like this color better. Did we get that right up here? Oh my goodness, look how much code we've written. Yeah, I like the other blue. I'm going to bring this down here. It's all about aesthetics in machine learning. It's not just numbers on a page. Daniel, how could you be so crass? Let's go there. Okay, that's a better color, red and blue. That's more lively, isn't it? So now let's convert to train and test, and then we can start to build a model with non-linearity. Oh, this is so good. Okay, convert data to tensors, and then to train and test splits. Nothing we haven't covered here before. So import torch, but it never hurts to practice code, right? Import torch from sklearn.model selection. Import train test split so that we can split our red and blue dots randomly. And we're going to turn data into tensors. And we'll go x equals torch from numpy, and we'll pass in x here. And then we'll change it into type torch.float. Why do we do this? Well, because, oh my goodness, autocorrect. It's getting the best of me here. You're watching me live code this stuff and battle with autocorrect. That's what this whole course is. Am I really teaching PyTorch, or am I just battling with Google Colab's autocorrect? We are turning it into torch.float with a type here because, why? NumPy's default, which is what Make Circles uses behind the scenes. NumPy is actually used in a lot of other machine learning libraries. Pandas, built on NumPy. Scikit-learn does a lot of NumPy. Matplotlib, NumPy. That's just showing the, what's the word? Is it ubiquitous? Ubiquity? I'm not sure, maybe. If not, you can correct me. The ubiquity of NumPy and test sets, but we're using PyTorch to leverage the power of autograd, which is what powers our gradient descent, and the fact that it can use GPUs. So we're creating train and test splits here with train test split x, y, and we're going to go test size equals 0.2, and we're going to set random state equals 42, and then we'll view our first 5 samples. Are these going to be tensors? Fingers crossed, we haven't got an error. Beautiful, we have tensors here. Okay, now we're up to the exciting part. We've got our data set back. I think it's time to build a model with non-linearity. So if you'd like to peek ahead, check out TorchNN again. This is a little bit of a spoiler. Go into the nonlinear activations, see if you can find the one that we've already used. That's your challenge. Can you find the one we've already used? And go into here and search what is a non-linear function. So give that a go and see what comes up. I'll see you in the next video. Welcome back. Now, put your hand up if you're ready to learn about non-linearity. And I know I can't see your hands up, but I better see some hands up, or I better feel some hands up, because my hand's up, because non-linearity is a magic piece of the puzzle that we're about to learn about. So let's title this section, Building a Model with Non-Linearity. So just to re-emphasize, linear equals straight lines, and in turn, non-linear equals non-straight lines. And I left off the end of the last video giving you the challenge of checking out the torch.nn module, looking for the non-linear function that we've already used. Now, where would you go to find such a thing? And oh, what do we have in here? Non-linear activations. And there's going to be a fair few things here, but essentially all of the modules within torch.nn are either some form of layer in a neural network. If we recall, let's go to a neural network. We've seen the anatomy of a neural network. Generally, you'll have an input layer and then multiple hidden layers and some form of output layer. Well, these multiple hidden layers can be almost any combination of what's in torch.nn. And in fact, they can almost be any combination of function you could imagine. Whether they work or not is another question. But PyTorch implements some of the most common layers that you would have as hidden layers. And they might be pooling layers, padding layers, activation functions, and they all have the same premise. They perform some sort of mathematical operation on an input. And so if we look into the non-linear activation functions, you might have found nn.sigmoid. Where have we used this before? There's a sigmoid activation function in math terminology. It takes some input x, performs this operation on it, and here's what it looks like if we did it on a straight line, but I think we should put this in practice. And if you want an example, well, there's an example there. All of the other non-linear activations have examples as well, but I'll let you go through all of these in your own time. Otherwise, we're going to be here forever. nn.relu is another common function. We saw that when we looked at the architecture of a classification network. So with that being said, how about we start to code a classification model with non-linearity? And of course, if you wanted to, you could look up what is a non-linear function if you wanted to learn more. Non-linear means the graph is not a straight line. Oh, beautiful. So that's how I'd learn about non-linear functions. But while we're here together, how about we write some code? So let's go build a model with non-linear activation functions. And just one more thing before, just to re-emphasize what we're doing here. Before we write this code, I just remembered, I've got a nice slide, which is the question we posed in the previous video, the missing piece, non-linearity. But the question I want you to think about is, what could you draw if you had an unlimited amount of straight, in other words, linear, and non-straight, non-linear lines? So we've seen previously that we can build a model, a linear model, to fit some data that's in a straight line, linear data. But when we're working with non-linear data, well, we need the power of non-linear functions. So this is circular data. And now this is only a 2D plot, keep in mind there. Whereas neural networks and machine learning models can work with numbers that are in hundreds of dimensions. Impossible for us humans to visualize, but since computers love numbers, it's a piece of cake to them. So from Torch import nn, we're going to create our first neural network with nonlinear activations. This is so exciting. So let's create a class here. We'll create circle model. We've got circle model v1 already. We're going to create circle model v2. And we'll inherit from nn.module. And then we'll write the constructor, which is the init function. And we'll pass in self here. And then we'll go self, or super, sorry. Too many S words. Dot underscore underscore init underscore. There we go. So we've got the constructor here. And now let's create a layer 1. Self.layer1 equals just the same as what we've used before. nn.linear. We're going to create this quite similar to the model that we've built before, except with one added feature. And we're going to create in features, which is akin to the number of X features that we have here. Again, if this was different, if we had 3 X features, we might change this to 3. But because we're working with 2, we'll leave it as that. We'll keep out features as 10, so that we have 10 hidden units. And then we'll go layer 2. nn.linear. Again, these values here are very customizable because why? Because they're hyperparameters. So let's line up the out features of layer 2, and we'll do the same with layer 3. Because layer 3 is going to take the outputs of layer 2, so it needs in features of 10, and we want layer 3 to be the output layer, and we want one number as output, so we'll set 1 here. Now, here's the fun part. We're going to introduce a non-linear function. We're going to introduce the ReLU function. Now we've seen sigmoid. ReLU is another very common one. It's actually quite simple, but let's write it out first. nn.relu. So remember, torch.nn stores a lot of existing nonlinear activation functions so that we don't necessarily have to code them ourselves. However, if we did want to code a ReLU function, let me show you, it's actually quite simple. If we dive into nn.relu, or ReLU, however you want to say it, I usually say ReLU, applies the rectified linear unit function element-wise. So that means element-wise on every element in our input tensor. And so it stands for rectified linear unit. And here's what it does. Basically, it takes an input. If the input is negative, it turns the input to 0, and it leaves the positive inputs how they are. And so this line is not straight. Now you could argue, yeah, well, it's straight here and then straight there, but this is a form of a non-linear activation function. So it goes zoom, boom. If it was linear, it would just stay straight there like that. But let's see it in practice. Do you think this is going to improve our model? Well, let's find out together, hey? Forward, we need to implement the forward method. And here's what we're going to do. Where should we put our nonlinear activation functions? So I'm just going to put a note here. ReLU is a nonlinear activation function. And remember, wherever I say function, it's just performing some sort of operation on a numerical input. So we're going to put a nonlinear activation function in between each of our layers. So let me show you what this looks like. Self.layer3. We're going to start from the outside in. Self.relu, and then we're going to go self.layer2. And then we're going to go self.relu. And then there's a fair bit going on here, but nothing we can't handle. Layer 1, and then here's the X. So what happens is our data goes into layer 1, performs a linear operation with nn.linear. Then we pass the output of layer 1 to a ReLU function. So where's ReLU up here? We turn all of the negative outputs of our model, of layer 1 to 0, and we keep the positives how they are. And then we do the same here with layer 2. And then finally, the outputs of layer 3 stay as they are. We've got out features there. We don't have a ReLU on the end here because we're going to pass the outputs to the sigmoid function later on. And if we really wanted to, we could put self.sigmoid here equals nn.sigmoid. But that's just one way of constructing it. We're just going to apply the sigmoid function to the logits of our model, because what are the logits? The raw output of our model. And so let's instantiate our model. This is going to be called model 3, which is a little bit confusing, but we're up to model 3, which is circle model v2. And we're going to send that to the target device. And then let's check model 3. What does this look like? Wonderful. So it doesn't actually show us where the ReLUs appear, but it just shows us what are the parameters of our circle model v2. Now, I'd like you to have a think about this, and my challenge to you is to go ahead and see if this model is capable of working on our data, on our circular data. So we've got the data sets ready. You need to set up some training code. My challenge to you is write that training code and see if this model works. But we're going to go through that over the next few videos. And also, my other challenge to you is to go to the TensorFlow playground and recreate our neural network here. You can have 2 hidden layers. Does this go to 10? Well, it only goes to 8. We'll keep this at 5. So build something like this. So we've got 2 layers with 5. It's a little bit different to ours because we've got 2 layers with 10. And then put the learning rate to 0.01. Well, what do we have? 0.1 with stochastic gradient descent. We've been using 0.1, so we'll leave that. So this is the TensorFlow playground. And then change the activation here. Instead of linear, which we've used before, change it to ReLU, which is what we're using. And press play here and see what happens. I'll see you in the next video. Welcome back. In the last video, I left off leaving the challenge of recreating this model here. It's not too difficult to do. We've got 2 hidden layers and 5 neurons. We've got our data set, which looks kind of like ours, but the main points here are I have to learning rate of 0.1, which is what we've been using, But to change it from, we've previously used a linear activation. To change it from linear to ReLU, which is what we've got set up here in the code. Now, remember, ReLU is a popular and effective nonlinear activation function. And we've been discussing that we need nonlinearity to model nonlinear data. And so that's the crux of what neural networks are. Artificial neural networks, not to get confused with the brain neural networks, but who knows? This might be how they work too. I don't know, I'm not a neurosurgeon or a neuroscientist. Artificial neural networks are a large combination of linear, so this is straight, and non-straight, non-linear functions, which are potentially able to find patterns in data. And so for our data set, it's quite small. It's just a blue and a red circle, but this same principle applies for larger data sets and larger models, combined linear and non-linear functions. So we've got a few tabs going on here. Let's get rid of some. Let's come back to here. Did you try this out? Does it work? Do you think it'll work? I don't know. Let's find out together. Ready? 3, 2, 1. Look at that! Almost instantly, the training loss goes down to 0 and the test loss is basically 0 as well. Look at that. That's amazing. We can stop that there. And if we change the learning rate maybe a little lower, let's see what happens. It takes a little bit longer to get to where it wants to go to. See, that's the power of changing the learning rate. Let's make it really small. What happens here? So that was about 300 epochs. The loss started to go down. If we change it to be really small, oh, we're getting a little bit of a trend. Is it starting to go down? We're already surpassed the epochs that we had. So see how the learning rate is much smaller? That means our model is learning much slower. So this is just a beautiful visual way of demonstrating different values of the learning rate. We could sit here all day and that might not get to lower, but let's increase it by 10x. And that was over 1,000 epochs and it's still at about 0.5, let's say. Oh, we got a better, oh, we're going faster already. So not even at 500 or so epochs, we're about 0.4. That's the power of the learning rate. We'll increase it by another 10x. We'll reset, start again. Oh, would you look at that? Much faster this time. That is beautiful. Oh, there is nothing better than watching a loss curve go down. In the world of machine learning, that is. And then we reset that again. And let's change it right back to what we had. And we get to 0 in basically under 100 epochs. So that's the power of the learning rate. Little visual representation. Speaking of learning rates, it's time for us to build an optimizer and a loss function. So let's write here. We've got our nonlinear model. Set up, loss, and optimizer. You might have already done this because the code, this is code that we've written before, but we're going to redo it for completeness and practice. So we want a loss function. We're working with logits here, and we're working with binary cross entropy. So what loss do we use? Binary cross entropy. Sorry, we're working with a binary classification problem. Blue dots or red dots. Torch.optim. What are some other binary classification problems that you can think of? We want model 3 dot parameters. They're the parameters that we want to optimize this model here. And we're going to set our LR to 0.1, just like we had in the TensorFlow playground. Beautiful. So some other binary classification problems I can think of would be email, spam or not spam, credit cards, so equals fraud or not fraud. What else? You might have insurance claims equals who's at fault or not at fault. If someone puts in a claim speaking about a car crash, whose fault was it? Was the person submitting the claim, were they at fault? Or was the person who was also mentioning the claim, are they not at fault? So there's many more, but they're just some I can think of off the top of my head. But now let's train our model with nonlinearity. Woohoo! Oh, we're on a roll here. Training a model with nonlinearity. So we've seen that if we introduce a nonlinear activation function within a model, remember this is a linear activation function, and if we train this, the loss doesn't go down. But if we just adjust this to add a ReLU in here, we get the loss going down. So hopefully this replicates with our pure PyTorch code. So let's do it, hey? So we're going to create random seeds. Because we're working with CUDA, we'll introduce the CUDA random seed as well. Torch.manual seed. Again, don't worry too much if your numbers on your screen aren't exactly what mine are. That's due to the inherent randomness of machine learning. In fact, stochastic gradient descent, stochastic again stands for random. We're just setting up the seeds here so that they can be as close as possible, but the direction is more important. So if my loss goes down, your loss should also go down on target device. And then we're going to go xtrain. So this is setting up device agnostic code. We've done this before, but we're going to do it again for completeness, just to practice every step of the puzzle. That's what we want to do. We want to have experience. That's what this course is. It's a momentum builder, so that when you go to other repos and machine learning projects that use PyTorch, you can go, oh, does this code set device agnostic code? What problem are we working on? Is it binary or multi-class classification? So let's go loop through data. Again, we've done this before, but we're going to set up the epochs. Let's do 1,000 epochs. Why not? So we can go for epoch in range epochs. What do we do here? Well, we want to train. So this is training code. We set our model3.train. And I want you to start to think about how could we functionize this training code. We're going to start to move towards that in a future video. So one is forward pass. We've got the logits. Why the logits? Well, because the raw output of our model without any activation functions towards the final layer, classified as logits or called logits. And then we create ypred, as in prediction labels, by rounding the output of torch.sigmoid of the logits. So this is going to take us from logits to prediction probabilities to prediction labels. And then we can go to, which is calculate the loss. That's from my unofficial PyTorch song. Calculate the loss. We go loss equals loss fn, y logits. Because remember, we've got BCE with logits loss and takes in logits as first input. And that's going to calculate the loss between our model's logits and the y training labels. And we will go here, we'll calculate accuracy using our accuracy function. And this one is a little bit backwards compared to PyTorch, but we pass in the y training labels first, but it's constructed this way because it's in the same style as scikit-learn. 3, we go optimizer 0 grad. We zero the gradients of the optimizer so that it can start from fresh, calculating the ideal gradients every epoch. So it's going to reset every epoch, which is fine. Then we're going to perform backpropagation. PyTorch is going to take care of that for us by calling loss backwards. And then we will perform gradient descent. So step the optimizer to see how we should improve our model parameters. So optimizer.step. Oh, and I want to show you, speaking of model parameters, let's check our model3.stateDict. So the relu activation function actually doesn't have any parameters. So you'll notice here, we've got weight, we've got bias of layer 1, layer 2, and a layer 3. So the relu function here doesn't have any parameters to optimize. If we go nn.relu, does it say what it implements? There we go. So it's just the maximum of 0 or x. So it takes the input and takes the max of 0 or x. And so when it takes the max of 0 or x, if it's a negative number, 0 is going to be higher than a negative number. So that's why it zeros all of the negative inputs. And then it leaves the positive inputs how they are, because the max of a positive input versus 0 is the positive input. So this has no parameters to optimize. That's why it's so effective, because you think about it, every parameter in our model needs some little bit of computation to adjust. And so the more parameters we add to our model, the more compute that is required. So generally, the kind of trade-off in machine learning is that, yes, more parameters have more of an ability to learn, but you need more compute. So let's go model3.eval, and we're going to go with torch.inference mode. If I could spell inference, that'd be fantastic. we're going to do what? We're going to do the forward pass. So test logits equals model3 on the test data. And then we're going to calculate the test pred labels by calling torch.round on torch.sigmoid on the test logits. And then we can calculate the test loss. How do we do that? Equals loss fn on test logits versus y test. And then we can also calculate the test accuracy. I'm just going to give myself some more space here so I can code in the middle of the screen. Equals accuracy function on what? We're going to pass in y true equals y test. And then we will pass in y pred equals test pred. Beautiful. A final step here is to print out what's happening. Now, this will be very important because, one, it's fun to know what your model's doing, and two, if our model does actually learn, I'd like to see the loss values go down and the accuracy values go up. As I said, there's nothing much more beautiful in the world of machine learning than watching a loss function go down, or a loss value go down, and watching a loss curve go down. So let's print out the current epoch, and then we'll print out the loss, which will just be the training loss, and we'll take that to 4 decimal places, and then we'll go accuracy here, and this will be acc, and we'll take this to 2 decimal places, and we'll put a little percentage sign there, and then we'll break it up by putting in the test loss here, and we'll put in the test loss. Because remember, our model learns patterns on the training data set and then evaluates those patterns on the test data set. So, and we'll pass in test acc here. And no doubt there might be an error or two within all of this code, but we're going to try and run this because we've seen this code before, but I think we're ready. We're training our first model here with non-linearities built into the model. You ready? 3, 2, 1, let's go. Oh, of course. Module torch CUDA has no attribute manuals are. Just a typo. Standard manual. There we go. Had to sound that out. Another one. What do we get wrong here? Oh, target size must be same as input size. Where did it mess up here? What do we get wrong? Test loss, test logits on y test. So these two aren't matching up. Model 3 X test and Y test. What's the size of... So let's do some troubleshooting on the fly, hey? Not everything always works out as you want. So length of X test. We've got a shape issue here. Remember how I said one of the most common issues in deep learning is a shape issue? So we've got the same shape here. Let's check test logits dot shape and y test dot shape. We'll print this out. So 200. Oh, here's what we have to do. That's what we missed. Dot squeeze. Ah, see how I've been hinting at the fact that we needed to call dot squeeze? So this is where the discrepancy is. Our test logits dot shape, we've got an extra dimension here. And what are we getting here? A value error on the target size, which is a shape mismatch. So we've got target size 200, must be the same input size as torch size 201. So, did we squeeze this? Oh, that's why the training worked. Okay, so we've missed this. Let's just get rid of this. So we're getting rid of the extra 1 dimension by using squeeze, which is the 1 dimension here. We should have everything lined up. There we go. Okay, oh, look at that. Yes! Our accuracy has gone up, albeit not by too much. It's still not perfect. Ideally, we'd like this to be towards 100% and the loss to be lower. But I feel like we've got a better performing model, don't you? Now, that is the power of non-linearity. All we did was we added in a ReLU layer, or just 2 of them. ReLU here. But what did we do? We gave our model the power of straight lines, straight linear, of straight lines, and non-straight lines. So it can potentially draw a line to separate these circles. So in the next video, let's draw a line, plot our model's decision boundary using our function, and see if it really did learn anything. I'll see you there. Welcome back. In the last video, we trained our first model, and as you can tell, I've got the biggest smile on my face, but we trained our first model that harnesses both the power of straight lines and non-straight lines, or linear functions and non-linear functions. And by the 1000th epoch, we look like we're getting a bit better results than just pure guessing, which is 50%, because we have 500 samples of red dots and 500 samples of blue dots. So we have evenly balanced classes. Now, we've seen that if we added a ReLU activation function with a dataset similar to ours with a TensorFlow playground, the model starts to fit, but it doesn't work with just linear. There's a few other activation functions that you could play around with here. You could play around with the learning rate, regularization. If you're not sure what that is, I'll leave that as extra curriculum to look up. But we're going to retire the TensorFlow playground for now because we're going to go back to writing code. So let's get out of that, and let's get out of that. We now have to evaluate our model because right now it's just numbers on a page. So let's write down here, 6.4. What do we like to do to evaluate things? It's visualize, visualize, visualize. So evaluating a model trained with nonlinear activation functions. And we also discussed the point that neural networks are really just a big combination of linear and nonlinear functions trying to draw patterns in data. So with that being said, let's make some predictions with our Model 3, our most recently trained model. We'll put it into eval mode, and then we'll set up inference mode. Inference mode, beautiful. And then we'll go ypreds equals torch.round, and then torch.sigmoid. We could functionize this, of course. Model 3, and then pass in xtest. And you know what? We're going to squeeze these here because we ran into some troubles in the previous video. I actually really liked that we did because then we got to troubleshoot a shape error on the fly, because that's one of the most common issues you're going to come across in deep learning. So ypreds, let's check them out, and then let's check out ytest. We want ytest 10. So remember, when we're evaluating predictions, we want them to be in the same format as our original labels. We want to compare apples to apples. And if we compare the format here, do these two things look the same? Yes, they do. They're both on CUDA and they're both floats. We can see that it's got this one wrong, whereas the other ones look pretty good. This might look pretty good if we visualize it. So now you might have already done this because I issued the challenge of plotting the decision boundaries. Plot decision boundaries, and let's go plt.figure. And we're going to set up the fig size to equal 12.6 because, again, one of the advantages of hosting a machine learning cooking show is that you can code ahead of time. And then we can go plt.title is train. And then we're going to call our plot decision boundary function, which we've seen before, plot decision boundary. And we're going to pass this one in. We could do model 3. But we could also pass it in our older models too, Model 1, that doesn't use non-linearity. In fact, I reckon that'll be a great comparison. So we'll also create another plot here for the test data, and this will be on index number 2. So remember, subplot is number of rows, number of columns, index where the plot appears. We'll give this one a title, plot.title. This will be test, and Google Colab, I didn't want that. As I said, this course is also a battle between me and Google Colab's autocorrect. So we'll go Model 3, and we'll pass in the test data here. And behind the scenes, our plot decision boundary function will create a beautiful graphic for us, perform some predictions on the X, the features input, and then we'll compare them with the Y values. Let's see what's going on here. Oh, look at that! Yes, our first nonlinear model. Okay, it's not perfect, but it is certainly much better than the models that we had before. Look at this. Model 1 has no linearity. Model 1 equals no non-linearity. I've got a double negative there. Whereas Model 3 equals has non-linearity. So do you see the power of non-linearity, or better yet, the power of linearity or linear straight lines with non-straight lines? So I feel like we could do better than this though. Here's your challenge, is can you improve Model 3 to do better? What did we get? 79% accuracy. to do better than 80% accuracy on the test data? I think you can. So that's the challenge. And if you're looking for hints on how to do so, where can you look? Well, we've covered this, improving a model. So maybe you add some more layers. Maybe you add more hidden units. Maybe you fit for longer. Maybe if you add more layers, you put a ReLU activation function on top of those as well. Maybe you lower the learning rate, because right now we've got 0.1. So give this a shot. Try and improve it. I think you can do it. But we're going to push forward. That's going to be your challenge for some extra curriculum. I think in the next section, we've seen our nonlinear activation functions in action. Let's write some code to replicate them. I'll see you there. Welcome back. In the last video, I left off with the challenge of improving Model 3 to do better than 80% accuracy on the test data. I hope you gave it a shot, but here are some of the things I would have done, is I'd potentially add more layers, and maybe increase the number of hidden units, and then if we needed to, fit for longer, and maybe lower the learning rate to 0.01. But I'll leave that for you to explore, because that's the motto of the data scientist, right? Is to experiment, experiment, experiment. So let's go in here. We've seen our nonlinear activation functions in practice. Let's replicate them. So replicating nonlinear activation functions. And remember, neural networks, rather than us telling the model what to learn, we give it the tools to discover patterns in data, and it tries to figure out the best patterns on its own. And what are these tools? Let's write down here. We've seen this in action. And these tools are linear and non-linear functions. So a neural network is a big stack of linear and non-linear functions. For us, we've only got about 4 layers or so, 4 or 5 layers. But as I said, other networks can get much larger. But the premise remains, some form of linear and non-linear manipulation of the data. So let's get out of this. Let's make our workspace a little bit more cleaner. Replicating nonlinear activation functions. So let's create a tensor to start with. Everything starts from the tensor. And we'll go A equals torch, a range. And we're going to create a range from -10 to 10 with a step of 1. And we can set the D type here to equal torch.float32, but we don't actually need to. That's going to be the default. So if we set A here, A.D type, then we've got torch float32, and I'm pretty sure if we got rid of that, oh, we've got torch int64. Huh, why is that happening? Well, let's check out A. Oh, it's because we've got integers as our values, because we have a step as 1. If we turn this into a float, what's going to happen? We get float32, but we'll keep it, otherwise this is going to be what, about 100 numbers? Yeah, nah, that's too many. Let's keep it at -10 to 10, and we'll set the D type here to torch float32. Beautiful. So it looks like PyTorch's default data type for integers is int64, but we're going to work with float32 because float32, if our data wasn't float32, with the functions we're about to create, we might run into some errors. So let's visualize this data. I want you to guess, is this a straight line or non-straight line? You've got 3 seconds. 1, 2, 3. Straight line. There we go. We've got -10 to +10 up here, or 9. Close enough. And so how would we turn this straight line? If it's a straight line, it's linear. How would we perform the ReLU activation function on this? Now, we could, of course, call torch ReLU on A. Actually, let's in fact just plot this. plt.plot on torch ReLU. What does this look like? Boom, there we go. But we want to replicate the ReLU function. So let's go nn.ReLU. What does it do? We've seen this before. So we need the max, we need to return, based on an input, we need the max of 0 and x. So let's give it a shot. We'll come here. Again, we need more space. There can never be enough code space here. I like writing lots of code. I don't know about you. But let's go ReLU. We'll take an input x, which will be some form of tensor, and we'll go return torch.maximum. I think you could just do torch.max, but we'll try maximum. Torch.tensor 0. So the maximum is going to return the max between whatever this is, one option, and whatever the other option is. So inputs must be tensors. So maybe we could just give a type hint here that this is torch.tensor. And this should return a tensor too. Return torch.tensor. Beautiful. You ready to try it out? Let's see what our relu function does. Relu A. Wonderful. It looks like we got quite a similar output to before. Here's our original A. So we've got negative numbers. There we go. So recall that the relu activation function turns all negative numbers into 0 because it takes the maximum between 0 and the input. And if the input's negative, well then 0 is bigger than it. And it leaves all of the positive values as they are. So that's the beauty of relu. Quite simple, but very effective. So let's plot relu activation function, our custom one. We will go plt.plot. We'll call our relu function on A. Let's see what this looks like. Oh, look at us go. Well done. Just the exact same as the torch relu function. Easy as that, hey? And what's another nonlinear activation function that we've used before? Well, I believe one of them is, if we go down to here, what did we say before? Sigmoid. Where is that? Where are you, Sigmoid? Here we go. Hello, Sigmoid. Ooh, this has got a little bit more going on here. 1 over 1 plus exponential of negative x. So sigmoid, or this little symbol for sigmoid, of x, which is an input, we get this. So let's try and replicate this. I might just bring this one in here. Right now, let's do the same for sigmoid. So what do we have here? Well, we want to create a custom sigmoid, and we want to have some sort of input, x, and we want to return 1 divided by, do we have the function in sigmoid? 1 divided by 1 plus exponential, 1 plus torch.exp for exponential on negative x. And we might put the bottom side in brackets so that it does that operation. I reckon that looks all right to me. So 1 divided by 1 plus torch exponential of negative x. Do we have that? Yes, we do. Well, there's only one real way to find out. Well, let's plot the torch version of sigmoid. Torch.sigmoid, and we'll pass in x. See what happens. And then, oh, we have A. My bad. A is our tensor. What do we get? We get a curved line. Wonderful. And then we go plt.plot, and we're going to use our sigmoid function on A. Did we replicate Torch's sigmoid function? Yes, we did. Woohoo! Now, see, this is what's happening behind the scenes with our neural networks. Of course, you could do more complicated activation functions or layers and whatnot, and you can try to replicate them. In fact, that's a great exercise to try and do. But we've essentially, across the videos and the sections that we've done, we've replicated our linear layer and we've replicated the ReLU. So we've actually built this model from scratch, or we could if we really wanted to, but it's a lot easier to use PyTorch's layers because we're building neural networks here like Lego bricks, stacking together these layers in some way, shape, or form. And because they're a part of PyTorch, we know that they've been error tested and they compute as fast as possible behind the scenes and use GPU, and we get a whole bunch of benefits. PyTorch offers a lot of benefits by using these layers rather than writing them ourselves. And so this is what our model is doing. It's literally like to learn these values and decrease the loss function and increase the accuracy. It's combining linear layers and non-linear layers or non-linear functions. Where's our ReLU function? Here. A ReLU function like this, behind the scenes. So just combining linear and non-linear functions to fit a data set. And that premise remains even on our small data set and on very large data sets and very large models. So with that being said, I think it's time for us to push on. We've covered a fair bit of code here, but we've worked on a binary classification problem. Have we worked on a multi-class classification problem yet? Do we have that here? Where's my fun graphic? We have multi-class classification. I think that's what we cover next. We're going to put together all of the steps in our workflow that we've covered for binary classification. But now let's move on to a multi-class classification problem. If you're with me, I'll see you in the next video. Welcome back. In the last few videos, we've been harnessing the power of non-linearity, specifically non-straight line functions, and we replicated some here. And we learned that a neural network combines linear and non-linear functions to find patterns in data. And for our simple red versus blue dots, once we added a little bit of non-linearity, we found the secret sauce to start separating our blue and red dots. And I also issued you the challenge to try and improve this, and I think you can do it. So hopefully you've given that a go. But now let's keep pushing forward. We're going to reiterate over basically everything that we've done, except this time from the point of view of a multi-class classification problem. So I believe we're up to section 8, putting it all together with a multi-class classification problem. Beautiful. And recall the difference between binary classification equals one thing or another, such as cat versus dog, if you were building a cat versus dog image classifier, spam versus not spam for, say, emails that were spam or not spam, or even internet posts on Facebook or Twitter or one of the other internet services, and then fraud or not fraud for credit card transactions, and then multi-class classification is more than one thing or another. So we could have cat versus dog versus chicken. So I think we've got all the skills to do this. Our architecture might be a little bit different for a multi-class classification problem, but we've got so many building blocks now, it's not funny. Let's clean up this and we'll add some more code cells. And just to reiterate, so we've gone over non-linearity. The question is, what could you draw if you had an unlimited amount of straight, linear, and non-straight, non-linear lines? I believe you could draw some pretty intricate patterns, and that is what our neural networks are doing behind the scenes. And so we also learned that if we wanted to just replicate some of these non-linear functions, some of the ones that we've used before, we could create a range. Linear activation is just the line itself. And then if we wanted to do sigmoid, we get this curl here. And then if we wanted to do relu, well, we saw how to replicate the relu function as well. These both are nonlinear. And of course, torch.nn has far more nonlinear activations where they came from, just as it has far more different layers. And you'll get used to these with practice, and that's what we're doing here. So let's go back to the keynote. So this is what we're going to be working on, multi-class classification. So there's one of the big differences here. We use the softmax activation function versus sigmoid. There's another big difference here. Instead of binary cross-entropy, we use just cross-entropy. But I think most of it's going to stay the same. We're going to see this in action in a second, but let's just describe our problem space. Just to go visual, we've covered a fair bit here. Well done, everyone. So binary versus multi-class classification. Binary, one thing or another, 0 or 1. Multi-class could be 3 things, could be 1,000 things, could be 5,000 things, could be 25 things. So more than one thing or another. But that's the basic premise we're going to go with. Let's create some data, hey? 8.1. Creating a toy multi-class dataset. And so to create our dataset, we're going to import our dependencies. We're going to re-import torch, even though we already have it, just for a little bit of completeness. And we're going to go matplotlib. So we can plot. As always, we like to get visual where we can. Visualize, visualize, visualize. We're going to import from scikit-learn.datasets. Let's get make blobs. Now, where would I get this from? So sklearn.datasets, what do we get? Toy datasets. Do we have classification? Toy datasets, do we have blobs? If we just go make scikit-learn classification datasets. What do we get? Here's one option. There's also make blobs. Beautiful. Make blobs. This is the code for that. So let's just copy this in here and make blobs. We're going to see this in action anyway. Make blobs. As you might have guessed, it makes some blobs for us. I like blobs. It's a fun word to say. Blobs. So we want train test split because we want to make a data set and then we want to split it into train and test. Let's set the number of hyperparameters. So set the hyperparameters for data creation. Now I got these from the documentation here. Number of samples, how many blobs do we want, how many features do we want. So say for example, we wanted 2 different classes, that would be binary classification. Say for example, you wanted 10 classes, you could set this to 10, and we're going to see what the others are in practice, but if you want to read through them, you can well and truly do that. So let's set up, we want num classes. Let's double what we've been working with. We've been working with 2 classes, red dots or blue dots. Let's step it up a notch. We'll go to 4 classes. Watch out everyone. And we're going to go number of features will be 2. So we have the same number of features. And then the random seed is going to be 42. You might be wondering why these are capitalized. Well, generally, if we do have some hyperparameters that we say set at the start of a notebook, you'll find it's quite common for people to write them as capital letters just to say that, hey, these are some settings that you can change. You don't have to, but I'm just going to introduce that anyway because you might stumble upon it yourself. So create multi-class data. We're going to use the make blobs function here. So we're going to create some X blobs, some feature blobs, and some label blobs. We'll see what these look like in a second. I know I'm just saying blobs a lot. But we pass in here, none samples. How many do we want? Let's create 1,000 as well. That could really be a hyperparameter, but we'll just leave that how it is for now. Number of features is going to be num features. Centers equals num classes. So we're going to create 4 classes because we've set up num classes equal to 4. And then we're going to go center standard deviation. We'll give them a little shake up, add a little bit of randomness in here. Give the clusters a little shake up. We'll mix them up a bit, make it a bit hard for our model. But we'll see what this does in a second. Random state equals random seed, which is our favorite random seed, 42. Of course, you can set it whatever number you want, but I like 42. Oh, and we need a comma here, of course. Beautiful. Now, what do we have to do here? Well, because we're using scikit-learn, and scikit-learn leverages NumPy, so let's turn our data into tensors. Turn data into tensors, and how do we do that? Well, we grab xblob, and we call torch from NumPy. From NumPy, if I could type, that would be fantastic. That's all right. We're doing pretty well today. Haven't made too many typos. We did make a few in a couple of videos before, but hey, I'm only human. So we're going to torch from NumPy, and we're going to pass in the y blob, and we'll turn it into torch.float, because remember NumPy defaults as float 64, whereas PyTorch likes float 32. So split into training and test, and we're going to create xblob train, y or xtest, xblob test. We'll keep the blob nomenclature here. Y blob train and y blob test. And here's again where we're going to leverage the train test split function from scikit-learn. So thank you for that, scikit-learn. X blob, and we're going to pass the y blob, so features, labels, X is the features, Y are the labels, and a test size. We've been using a test size of 20%. That means 80% of the data will be for the training data. That's a fair enough split with our data set. And we're going to set the random seed to random seed, because normally train test split is random, but because we want some reproducibility here, we're passing random seeds. Finally, we need to get visual. So let's plot the data. Right now we've got a whole bunch of code and a whole bunch of talking, but not too much visuals going on. So we'll write down here, visualize, visualize, visualize. And we can call in plot.figure. What size do we want? I'm going to use my favorite hand in poker, which is 10:7, because it's generally worked out to be a good plot size for, in my experience anyway. We'll go xblob, and we want the 0th index here, and then we'll grab xblob as well. And you might notice that we're visualizing the whole data set here. That's perfectly fine. We could visualize train and test separately if we really wanted to, but I'll leave that as a little challenge to you. And we're going to go red, yellow, blue. Wonderful. What did we get wrong? Oh, of course we got something wrong. Center STD. Did we spell center wrong? Cluster STD. That's what I missed. So cluster STD. Standard deviation. What do we get wrong? Random seed. Oh, this needs to be random state. Oh, another typo. You know what? Just as I said I wasn't getting too many typos, I get 3. There we go. Look at that. Our first multi-class classification data set. So if we set this to 0, what does it do to our clusters? Just take note of what's going on here, particularly the space between all of the dots. Now, if we set this cluster STD to 0, what happens? We get dots that are really just, look at that. That's too easy. Let's mix it up, all right? Now, you can pick whatever value you want here. I'm going to use 1.5 because now we need to build a model that's going to draw some lines between these 4 colors, 2 axes, 4 different classes. But it's not going to be perfect because we've got some red dots that are basically in the blue dots. And so, what's our next step? Well, we've got some data ready. It's now time to build a model. So, I'll see you in the next video. Let's build our first multi-class classification model. Welcome back. In the last video, we created a multi-class classification dataset using scikit-learn's makeblobs function. And now, why are we doing this? Well, because we're going to put all of what we've covered so far together. But instead of using binary classification or working with binary classification data, we're going to do it with multi-class classification data. So with that being said, let's get into building a multi-class classification model. So we'll create a little heading here. Building a multi-class classification model in PyTorch. And now I want you to have a think about this. We spent the last few videos covering non-linearity. Does this data set need non-linearity? As in, could we separate this data set with pure straight lines, or do we need some non-straight lines as well? Have a think about that. It's okay if you're not sure. We're going to be building a model to fit this data anyway, or draw patterns in this data anyway. And now, before we get into coding a model, so for multi-class classification, we've got this. For the input layer shape, we need to define the in features. So how many in features do we have? For the hidden layers, well, we could set this to whatever we want, but we're going to keep it nice and simple for now. For the number of neurons per hidden layer, again, this could be almost whatever we want, but because we're working with a relatively small data set, we've only got 4 different classes, we've only got 1,000 data points, we'll keep it small as well, but you could change this. Remember, you can change any of these because they're hyperparameters. For the output layer shape, well, how many output features do we want? We need 1 per class. How many classes do we have? We have 4 clusters of different dots here, so we'll need 4 output features. And then if we go back, we have an output activation of softmax. We haven't seen that yet. And then we have a loss function. Rather than binary cross entropy, we have cross entropy. And then optimizer as well is the same as binary classification. 2 of the most common are SGD, stochastic gradient descent, or the atom optimizer. But of course, the torch.optim package has many different options as well. So let's push forward and create our first multi-class classification model. First, we're going to get into the habit of creating device agnostic code. And we'll set the device here, equals CUDA. Nothing we haven't seen before, but again, we're doing this to put it all together so that we have a lot of practice. Is available, else CPU, and let's go device. So we should have a GPU available. Beautiful, CUDA. Now, of course, if you don't, you can go change runtime type, select GPU here. That will restart the runtime. You'll have to run all of the code that's before this cell as well, but I'm going to be using a GPU. You don't necessarily need one because our data set's quite small and our models aren't going to be very large, but we set this up so we have device agnostic code. And so let's build a multi-class classification model. Ooh, look at us go. Just covering all of the foundations of classification in general here. And we now know that we can combine linear and non-linear functions to create neural networks that can find patterns in almost any kind of data. So I'm going to call my class here blob model, and it's going to, of course, inherit from nn.module. And we're going to upgrade our class here. We're going to take some inputs here, and I'll show you how to do this. If you're familiar with Python classes, you would have already done stuff like this, but we're going to set some parameters for our models, because as you write more and more complex classes, you'll want to take inputs here. And I'm going to pre-build or preset the hidden units parameter to 8. Because I've decided, you know what, I'm going to start off with 8 hidden units, and if I wanted to change this to 128, I could. But in the constructor here, we've got some options. So we have input features. We're going to set these programmatically as inputs to our class when we instantiate it. The same with output features as well. And so here we're going to call self, super, sorry. I always get this mixed up. .init and underscore underscore. Beautiful. So we could do a doc string here as well. So let's write in this. Initializes multi-class classification. If I could spell classification model. Oh, this is great. And then we have some args here. This is just a standard way of writing doc strings. If you want to find out, this is Google Python docstring guide. There we go, Google Python style guide. This is where I get mine from. You can scroll through this. This is just a way to write Python code. Yeah, there we go. So we've got a little sentence saying what's going on. We've got args, we've got returns, and we've got errors if something's going on. So I highly recommend checking that out. Just a little tidbit. So this is if someone was to use our class later on, they know what the input features are. Input features, which is an int, which is number of input features to the model. And then, of course, we've got output features, which is also an int, which is number of output features of the model. And we've got the red line here is telling us we've got something wrong, but that's okay. And then the hidden features, this is number of output classes for the case of multi-class classification. And then the hidden units, int, and then number of hidden units between layers. And then the default is 8. Beautiful. And then under that, we'll just do that. Is that going to fix itself? Yeah, there we go. We could put in what it returns whatever it returns, and then an example use case, but I'll leave that for you to fill out if you like. So let's instantiate some things here. What we might do is write self.linear layer stack, and we will set this as nn.sequential. Oh, we haven't seen this before, but we're just going to look at a different way of writing a model here. Previously, when we created a model, what did we do? Well, we instantiated each layer as its own parameter here, and then we called on them one by one, but we did it in a straightforward fashion. So that's why we're going to use sequential here to just step through our layers. We're not doing anything too fancy, so we'll just set up a sequential stack of layers here. And recall that sequential just steps through, passes the data through each one of these layers one by one. And because we've set up the parameters up here, input features can equal to input features. And output features, what is this going to be? Is this going to be output features, or is this going to be hidden units? It's going to be hidden units because it's not the final layer. We want the final layer to output our output features. So input features, this will be hidden units because remember, the subsequent layer needs to line up with the previous layer. Output features, we're going to create another one that outputs hidden units. and then we'll go nn.linear. In features equals hidden units because it takes the output features of the previous layer. So as you see here, the output features of this feeds into here. The output features of this feeds into here. And then finally, this is going to be our final layer. We'll do 3 layers. Output features equals output features. Wonderful. So how do we know the values of each of these? Well, let's have a look at xtrain.shape and ytrain.shape. So in the case of x, we have 2 input features, and in the case of y, well, this is a little confusing as well because y is a scalar, but what do you think the values for y are going to be? Well, let's go np, or is there torch.unique? I'm not sure. Let's find out together, hey? Torch unique, 0 and 1, ytrain. Oh, we need y blob train, that's right, blog. I'm too used to writing blog, blob. And we need blob train, but I believe it's the same here. And then blob. There we go. So we have 4 classes, so we need an output features value of 4. And now if we wanted to add non-linearity here, we could put it in between our layers here like this. But I asked the question before, do you think that this data set needs non-linearity? Well, let's leave it in there to begin with. And one of the challenges for you, oh, do we need commas here? I think we need commas here. One of the challenges for you will be to test the model with non-linearity and without non-linearity. So let's just leave it in there for the time being. What's missing from this? Well, we need a forward method. So def forward self x. What can we do here? Well, because we've created this as a linear layer stack using nn.sequential, we can just go return linear layer stack and pass it x. And what's going to happen? Whatever input goes into the forward method is just going to go through these layers sequentially. Oh, we need to put self here because we've initialized it in the constructor. Beautiful. And now let's create an instance of blob model and send it to the target device. We'll go model4 equals blob model, and then we can use our input features parameter, which is this one here, and we're going to pass it a value of what? 2, and then output features. Why? Because we have 2 x features. Now the output features is going to be the same as the number of classes that we have. 4. If we had 10 classes, we'd set it to 10. So we'll go 4. And then the hidden units is going to be 8 by default. So we don't have to put this here, but we're going to put it there anyway. And then, of course, we're going to send this to device. And then we're going to go model 4. What did we get wrong here? Unexpected keyword argument. Output features. Did we spell something wrong? No doubt we've got a spelling mistake. Output features. Output features? Oh, out features. Ah. That's what we needed. Out features, not output. I got a little confused there. Okay. There we go. Okay, beautiful. So just recall that the parameter here for nn.linear, did you pick up on that? Is out features, not output features. Output features, a little confusing here, is our final layer, our output layer's number of features there. So we've now got a multi-class classification model that lines up with the data that we're using. So the shapes line up. Beautiful. Well, what's next? Well, we have to create a loss function and, of course, a training loop. So I'll see you in the next few videos, and let's do that together. Welcome back. In the last video, we created our multi-class classification model. And we did so by subclassing nn.module, and we set up a few parameters for our class constructor here, so that when we made an instance of the blob model, we could customize the input features, the output features. Remember, this lines up with how many features X has, and the output features here lines up with how many classes are in our data. So if we had 10 classes, we could change this to 10 and it would line up. And then if we wanted 128 hidden units, well, we could change that. So we're getting a little bit more programmatic with how we create models here. And as you'll see later on, a lot of the things that we've built in here can also be functionized in a similar manner. But let's keep pushing forward. What's our next step? If we build a model, if we refer to the workflow, you'd see that we have to create a loss function and an optimizer for a multi-class classification model. And so what's our option here for creating a loss function? Where do we find loss functions in PyTorch? I'm just going to get out of this and I'll make a new tab here. And if we search torch.nn, because torch.nn is the basic building blocks for graphs, in other words, neural networks, where do we find loss functions? Here we go. Beautiful. So we've seen that L1 loss or MSE loss could be used for regression predicting a number. And I'm here to tell you as well that for classification, we're going to be looking at cross-entropy loss. Now, this is for multi-class classification. For binary classification, we work with BCE loss. And of course, there's a few more here, but I'm going to leave that as something that you can explore on your own. Let's jump in to cross-entropy loss. So what do we have here? This criterion computes. Remember, a loss function in PyTorch is also referred to as a criterion. You might also see loss function referred to as cost function, C-O-S-T, but I call them loss functions. So this criterion computes the cross-entropy loss between input and target. Okay, so the input is something, and the target is our target labels. It is useful when training a classification problem with C classes. There we go. So that's what we're doing. We're training a classification problem with C classes. C is a number of classes. If provided, the optional argument weight should be a 1D tensor assigning a weight to each of the classes. So we don't have to apply a weight here, but why would you apply a weight? Well, it says, if we look at weight here, this is particularly useful when you have an unbalanced training set. So just keep this in mind as you're going forward. If you wanted to train a data set that has imbalanced samples, in our case, we have the same number of samples for each class, but sometimes you might come across a data set with maybe you only have 10 yellow dots, and maybe you have 500 blue dots and only 100 red and 100 light blue dots. So you have an imbalanced data set. So that's where you can come in and have a look at the weight parameter here. But for now, we're just going to keep things simple. We have a balanced data set, and we're going to focus on using this loss function. If you'd like to read more, please, you can read on here. And if you wanted to find out more, you could go, what is cross-entropy loss? And I'm sure you'll find a whole bunch of loss functions. There we go. There's the ML cheat sheet. I love that. The ML glossary. That's one of my favorite websites. Towards Data Science, you'll find that website. Wikipedia. Machine Learning Mastery is also another fantastic website. But you can do that all in your own time. Let's code together, hey? We'll set up a loss function. Oh, and one more resource before we get into code is that we've got the architecture, well, the typical architecture of a classification model. The loss function for multi-class classification is cross-entropy, or torch.nn.cross-entropy loss. Let's code it out. If in doubt, code it out. So create a loss function for multi-class classification. And then we go loss fn equals nn.cross-entropy loss. Beautiful. And then we want to create an optimizer. Create an optimizer for multi-class classification. And now the beautiful thing about optimizers is they're quite flexible. They can go across a wide range of different problems. So the optimizer, so two of the most common, and I say most common because they work quite well across a wide range of problems. So that's why I've only listed two here. But of course, within the torch.optim module, you will find a lot more different optimizers. But let's stick with SGD for now. And we'll go back. We'll go optimizer equals torch.optim for optimizer, SGD for stochastic gradient descent. The parameters we want our optimizer to optimize. Model 4. We're up to our fourth model already. Oh my goodness. Model 4.parameters. And we'll set the learning rate to 0.1. Of course, you could change the learning rate if you wanted to. In fact, I'd encourage you to see what happens if you do, because why? The learning rate is a hyperparameter. I'm better at writing code than I am at spelling. You can change. Wonderful. So we've now got a loss function and an optimizer for a multi-class classification problem. What's next? Well, we could start to building a training loop. We could start to do that, but I think we have a look at what the outputs of our model are. So more specifically, getting prediction probabilities for a multi-class PyTorch model. So my challenge to you before the next video is to have a look at what happens if you pass xblob test through a model. And remember, what is a model's raw outputs? What is that referred to as? Well, I'll let you have a think about that before the next video. I'll see you there. Welcome back. In the last video, we created a loss function and an optimizer for our multi-class classification model. And recall, the loss function measures how wrong our model's predictions are, and the optimizer updates our model parameters to try and reduce the loss. So that's what that does. And I also issued the challenge of doing a forward pass with model 4, which is the most recent model that we created. And oh, did I just give you some code that wouldn't work? Did I do that on purpose? Maybe, maybe not. You'll never know. So if this did work, what are the raw outputs of our model? Let's get some raw outputs of our model. And if you recall, the raw outputs of a model are called logits. So we got a runtime error. Expected all tensors to be on the same device. Oh, of course. Why did this come up? Well, because if we go next, model 4 dot parameters, and if we check device, what happens here? Oh, we need to bring this in. Our model is on the CUDA device, whereas our data is on the CPU still. Can we go X? Is our data a tensor? Can we check the device parameter of that? I think we can. I might be proven wrong here. Oh, it's on the CPU. Of course we're getting a runtime error. Did you catch that one? If you did, well done. So let's see what happens. But before we do a forward pass, how about we turn our model into a val mode to make some predictions with torch.inference mode. We'll make some predictions. We don't necessarily have to do this because it's just test, but it's a good habit. Oh, y preds equals, what do we get? Y preds, and maybe we'll just view the first 10. What do we get here? Oh my goodness, a whole bunch of numbers on a page. Is this the same format as our data or our test labels? Let's have a look. No, it's not. Okay. Oh, we need Y blob test. Excuse me. I'm going to make that mistake a fair few times here. So we need to get this into the format of this. How can we do that? Now, I want you to notice one thing as well, is that we have one value here per one value, except that this is actually 4 values. Now, why is that? We have 1, 2, 3, 4. Well, that is because we set the out features up here. Our model outputs 4 features per sample. So each sample right now has 4 numbers associated with it. And what are these called? These are the logits. Now, what we have to do here, so let's just write this down. In order to evaluate and train and test our model, we need to convert our model's outputs which are logits, to prediction probabilities, and then to prediction labels. So we've done this before, but for binary classification. So we have to go from logits to pred probs to pred labels. All right, I think we can do this. So we've got some logits here. Now, how do we convert these logits to prediction probabilities? Well, we use an activation function. And if we go back to our architecture, what's our output activation here? For a binary classification, we use sigmoid. But for multi-class classification, this is the 2 main differences between multi-class classification and binary classification. One uses softmax, one uses cross entropy. And it's going to take a little bit of practice to know this off by heart. It took me a while, but that's why we have nice tables like this, and that's why we write a lot of code together. So we're going to use the softmax function here to convert our logits, our model's raw outputs, which is this here, to prediction probabilities. And let's see that. So convert our model's logit outputs to prediction probabilities. So let's create y-pred probs. So I like to call prediction probabilities pred probs for short. So torch.softmax, and then we go y logits, and we want it across the first dimension. So let's have a look. If we print y logits, we'll get the first 5 values there. And then look at the conversion here. Y logits, or y pred probs. That's what we want to compare. Pred probs 5. Let's check this out. Oh, what did we get wrong here? Y logits. Do we have y logits? Oh no. We should change this to y logits because really that's the raw output of our model here. Y logits, let's rerun that. Check that. We know that these are different to these, but we ideally want these to be in the same format as these, our test labels. These are our model's predictions. And now we should be able to convert. There we go. Okay, beautiful. What's happening here? Let's just get out of this. And we will add a few code cells here so we have some space. Now, if you wanted to find out what's happening with torch.softmax, what could you do? We could go torch softmax, see what's happening. Softmax. Okay, so here's the function that's happening. We replicated some nonlinear activation functions before. So if you wanted to replicate this, what could you do? Well, if in doubt, code it out. You could code this out. You've got the tools to do so. We've got softmax to some x input, takes the exponential of x, so torch exponential over the sum of torch exponential of x. So I think you could code that out if you wanted to, but let's for now just stick with what we've got. We've got some logits here, and we've got some softmax, some logits that have been passed through the softmax function. So that's what's happened here. We've passed our logits as the input here, and it's gone through this activation function. These are prediction probabilities. And you might be like, Daniel, these are still just numbers on a page. But you'll also notice that none of them are negative. Okay, and there's another little tidbit about what's going on here. If we sum one of them up, let's get the first one. Will this work? And if we go torch.sum, what happens? Oh, they all sum up to 1. So that's one of the effects of the softmax function. And then if we go torch.max of y-pred probs, so this is a prediction probability. For multiclass, you'll find that for this particular sample here, the 0th sample, this is the maximum number. And so our model, what this is saying is our model is saying, this is the prediction probability, this is how much I think it is class 0. This number here, it's in order. This is how much I think it is class 1. This is how much I think it is class 2. This is how much I think it is class 3. And so we have one value for each of our 4 classes. A little bit confusing because it's 0th indexed. But the maximum value here is this index. And so how would we get the particular index value of whatever the maximum number is across these values? Well, we can take the argmax, and we get tensor 1. So for this particular sample, this one here, our model and these guesses or these predictions aren't very good. Why is that? Well, because our model is still just predicting with random numbers. We haven't trained it yet. So this is just random output here, basically. But for now, the premise still remains that our model thinks that for this sample, using random numbers, it thinks that index 1 is the right class, or class number 1. For this particular sample. And then for this next one, what's the maximum number here? I think it would be the 0th index. And the same for the next one. What's the maximum number here? Well, it would be the 0th index as well. But of course, these numbers are going to change once we've trained our model. So how do we get the maximum index value of all of these? So this is where we can go convert our model's prediction probabilities to prediction prediction labels. So let's do that. We can go ypreds equals torch.argmax on ypred probs, and if we go across the first dimension as well. So now let's have a look at ypreds. Do we have prediction labels in the same format as our yblob test? Beautiful, yes we do. Although many of them are wrong, as you can see. Ideally they would line up with each other, but because our model is predicting or making predictions with random numbers, so our model hasn't been trained, all of these are basically random outputs. So hopefully once we train our model, it's going to line up, the values of the predictions are going to line up with the values of the test labels. But that is how we go from our model's raw outputs to prediction probabilities to prediction labels for a multi-class classification problem. So let's just add the steps here. Logits, raw output of the model. Pred probs, to get the prediction probabilities, use torch.softmax, or the softmax activation function. Pred labels, take the argmax of the prediction probabilities. So we're going to see this in action later on when we evaluate our model, but I feel like now that we know how to go from logits to prediction probabilities to pred labels, we can write a training loop. So let's set that up. 8.5, create a training loop and testing loop for a multi-class PyTorch model. This is so exciting. I'll see you in the next video. Let's build our first training and testing loop for a multi-class PyTorch model. And I'll give you a little hint. It's quite similar to the training and testing loops we've built before, so you might want to give it a shot. I think you can. Otherwise, we'll do it together in the next video. Welcome back. In the last video, we covered how to go from raw logits, which is the output of the model, the raw output of the model for a multi-class PyTorch model. Then we turned our logits into prediction probabilities using torch.softmax. And then we turn those prediction probabilities into prediction labels by taking the argmax, which returns the index of where the maximum value occurs in the prediction probability. So for this particular sample, with these 4 values, because it outputs 4 values because we're working with 4 classes, if we were working with 10 classes, it would have 10 values. The principle of these steps would still be the same. So for this particular sample, this is the value that's the maximum. So we would take that index, which is 1. For this one, the index 0 has the maximum value. For this sample, same again, and then same again. I mean, these prediction labels are just random, right? So they're quite terrible. But now we're going to change that because we're going to build a training and testing loop for our multi-class model. Let's do that. So fit the multi-class model to the data. Let's go set up some manual seeds. Torch.manual seed. Again, don't worry too much if our numbers on the page are not exactly the same. That's inherent to the randomness of machine learning. We're setting up the manual seeds to try and get them as close as possible, but these do not guarantee complete determinism, which means the same output, but we're going to try. The direction is more important. Set number of epochs. We're going to go epochs. How about we just do 100? I reckon we'll start with that. We can bump it up to 1,000 if we really wanted to. Let's put the data to the target device. What's our target device? Well, it doesn't really matter because we've set device agnostic code. So whether we're working with a CPU or a GPU, our code will use whatever device is available. I'm typing blog again. So we've got X blob train, Y blob train. This is going to go where? It's going to go to the device. And Y blob train to device. And we're going to go X blob test. And then Y blob test equals X blob test to device. Otherwise, we'll get device issues later on. And we'll send this to device as well. Beautiful. Now what do we do now? Well, we loop through data. Loop through data. So for an epoch in range epochs for an epoch in a range. Epochs, I don't want that autocorrect. Come on, Google Colab, work with me here. We're training our first multi-class classification model. This is serious business. No, I'm joking. It's actually quite fun. So model4.train, and let's do the forward pass. I'm not going to put much commentary here because we've been through this before, but what are the logits? The logits are raw outputs of our model. So we'll just go xblobtrain and xtest. I didn't want that. xblobtrain, why did that do that? I need to turn off autocorrect in Google Colab. I've been saying it for a long time. ypred equals torch.softmax. So what are we doing here? We're going from logits to prediction probabilities here. So torch softmax y logits across the first dimension. And then we can take the argmax of this and dim equals 1. In fact, I'm going to show you a little bit of, oh, I've written blog here. Maybe autocorrect would have been helpful for that. A little trick, you don't actually have to do the torch softmax. The logits, if you just took the argmax of the logits, is a little test for you. Just take the argmax of the logits and see, do you get the same similar outputs as what you get here? So I've seen that done before, but for completeness, we're going to use the softmax activation function because you'll often see this in practice. And now what do? We calculate the loss. So the loss Fn, we're going to use categorical cross entropy here, or just cross entropy loss. So if we check our loss function, what do we have? We have cross entropy loss. We're going to compare our model's logits to yblob train. And then what are we going to do? We're going to calculate the accuracy because we're working with a classification problem. It'd be nice if we had accuracy as well as loss. Accuracy is one of the main classification evaluation metrics. ypred equals ypred. And now what do? Well, we have to zero grad the optimizer. Optimizer zero grad. Then we go loss backward. And then we step the optimizer. Optimizer step, step, step. So none of these steps we haven't covered before. We do the forward pass, we calculate the loss and any evaluation metric we choose to do so. We zero the optimizer, we perform backpropagation on the loss, and we step the optimizer. The optimizer will hopefully behind the scenes update the parameters of our model to better represent the patterns in our training data. And so we're going to go testing code here. What do we do for testing code? Well, or inference code. We set our model to eval mode. That's going to turn off a few things behind the scenes that our model doesn't need, such as dropout layers, which we haven't covered, but you're more than welcome to check them out if you go torch nn. Dropout layers, do we have dropout? Dropout layers, beautiful. And another one that it turns off is batch norm. Beautiful. And also you could search this. What does model.eval do? And you might come across Stack Overflow question, one of my favorite resources. So there's a little bit of extra curriculum, but I prefer to see things in action. So with torch inference mode, again, this turns off things like gradient tracking and a few more things. So we get as fast as code as possible because we don't need to track gradients when we're making predictions. We just need to use the parameters that our model has learned. We want xblob test to go to our model here for the test logits, and then for the test preds, we're going to do the same step as what we've done here. We're going to go torch.softmax on the test logits across the first dimension, and we're going to call the argmax on that to get the index value of where the maximum prediction probability value occurs. We're going to calculate the test loss or loss function. We're going to pass in what? The test logits here. Then we're going to pass in yblob test, compare the test logits. Behind the scenes, our loss function is going to do some things that convert the test logits into the same format as our test labels, and then return us a value for that. Then we'll also calculate the test accuracy here by passing in the ytrue as yblob test. And we have the ypred equals ypred. Wonderful. And then what's our final step? Well, we want to print out what's happening, because I love seeing metrics as our model trains. It's one of my favorite things to watch. If we go if epoch, let's do it every 10 epochs because we've got 100 so far, equals 0. Let's print out a nice F string with epoch. And then we're going to go loss. What do we put in here? We'll get our loss value, but we'll take it to 4 decimal places. And we'll get the training accuracy, which will be acc. And we'll take this to 2 decimal places. And we'll get a nice percentage sign there. And we'll go test loss equals test loss. And we'll go there. And finally, we'll go test acc at the end here. Test acc. Now, I'm sure by now, we've written a fair few of these. You're either getting sick of them, or you're like, wow, I can actually do the steps through here. And so don't worry, we're going to be functionizing all of this later on, but I thought I'm going to include them as much as possible so that we can practice as much as possible together. So you ready? We're about to train our first multi-class classification model. In 3, 2, 1, let's go. No typos. Oh, of course. What did we get wrong here? Oh, this is a fun error. Runtime error. NLL loss forward reduce CUDA kernel 2D index not implemented for float. Okay, that's a pretty full-on bunch of words there. I don't really know how to describe that, but here's a little hint. We've got float there. So we know that float is what? Float is a form of data. It's a data type. So potentially, because that's our hint, we said not implemented for float, so maybe we've got something wrong up here. Our data is of the wrong type. Can you see anywhere where our data might be the wrong type? Well, let's print it out. Where's our issue? Here. Y logits, Y blob train. Okay, Y blob train and Y logits. What does Y blob train look like? Y blob train. Okay, and what's the D type here? Float. Okay, so it's not implemented for float. Maybe we have to turn them into a different data type. What if we went type torch long tensor? What happens here? Expected all tensors to be on the same device, but found at least 2 devices. Oh my goodness, what have we got wrong here? Type torch long tensor. Friends, guess what? I found it. And so it was to do with this pesky little data type issue here. So if we run this again, and now this one took me a while to find, and I want you to know that behind the scenes, even though, again, this is a machine learning cooking show, it still takes a while to troubleshoot code, and you're going to come across this. But I thought, rather than spend 10 minutes doing it in a video, I'll show you what I did. So we went through this, and we found that, there's something going on here. I don't quite know what this is, and that seems quite like a long string of words, not implemented for float. And then we looked back at the line where it went wrong, and so that we know that maybe the float is hinting at that one of these 2 tensors is of the wrong data type. Now, why would we think that it's the wrong data type? Well, because anytime you see float or int or something like that, it generally hints at one of your data types being wrong. And so the error is actually right back up here where we created our tensor data. So we turned our labels here into floats, which generally is okay in PyTorch. However, this one should be of type torch.long tensor, which we haven't seen before, but if we go into torch long tensor, let's have a look. Torch.tensor. Do we have long tensor? Here we go. 64-bit integer signed. So why do we need torch.long tensor? And again, this took me a while to find, so I want to express this, that in your own code, you probably will butt your head up against some issues and errors that do take you a while to find, and data types is one of the main ones. But if we look in the documentation for cross-entropy loss, the way I kind of found this out was this little hint here. The performance of the criterion is generally better when the target contains class indices, as this allows for optimized computation. But I read this and it says target contains class indices. And I'm like, ours are indices already, but maybe they should be integers and not floats. But then if you actually just look at the sample code, you would find that they use dtype equals torch.long. Now, that's the thing with a lot of code around the internet, is that sometimes the answer you're looking for is a little bit buried. But if in doubt, run the code and butt your head up against a wall for a bit and keep going. So let's just rerun all of this and see, do we have an error here? Let's train our first multi-class classification model together. No errors, fingers crossed. Oh, what did we get wrong here? Okay, so we've got different size. We're slowly working through all of the errors in deep learning here. Value error, input batch size 200 to match target size 200. So this is telling me maybe our test data, which is of size 200, is getting mixed up with our training data, which is of size 800. So we've got test loss, the test logits, model 4. What's the size? Let's print out print test logits.shape and y-blob test. So troubleshooting on the fly here, everyone. What do we got? Torch size 800. Where are our test labels coming from? Y-blob test equals, oh, there we go. Did you catch that before? Maybe you did, maybe you didn't, but I think we should be right here. Now, if we just comment out this line, so we've had a data type issue and we've had a shape issue. Two of the main in machine learning. Oh, and again, we've had some issues. Y-blob test, what's going on here? I thought we just changed the shape. Oh no, we have to go up and reassign it again because now this is definitely Y-blob, yes. Let's rerun all of this, reassign our data. We are running into every single error here, but I'm glad we're doing this because otherwise you might not see how to troubleshoot these type of things. So the size of a tensor must match the size. Oh, we're getting the issue here. Oh, test preds. Oh my goodness, we have written so much code here. Test pred. So instead of y pred, this should be test preds. Fingers crossed. Are we training our first model yet or what? There we go. Okay, and we're printing out some stuff. I don't really want to print out that stuff, and I want to see the loss go down, so I'm going to... So friends, I hope you know that we've just been through some of the most fundamental troubleshooting steps, and you might say, oh, Daniel, that's a cop-out because you're just coding wrong, and in fact, I code wrong all the time. But we've now worked out how to troubleshoot them, shape errors and data type errors. But look at this! After all of that... Thank goodness, our loss and accuracy go in the directions that we want them to go. So our loss goes down and our accuracy goes up. Beautiful. So it looks like that our model is working on a multi-class classification data set. So how do we check that? Well, we're going to evaluate it in the next step by visualize, visualize, visualize. So you might want to give that a shot. See if you can use our plot decision boundary function. We'll use our model to separate the data here. So it's going to be much the same as what we did for binary classification, but this time we're using a different model and a different data set. I'll see you there. Welcome back. In the last video, we went through some of the steps that we've been through before in terms of training and testing a model, but we also butted our heads up against two of the most common issues in machine learning and deep learning in general, and that is data type issues and shape issues, but luckily we were able to resolve them. And trust me, you're going to run across many of them in your own deep learning and machine learning endeavors. So I'm glad that we got to have a look at them and sort of I could show you what I do to troubleshoot them. But in reality, it's a lot of experimentation. Run the code, see what errors come out, Google the errors, read the documentation, try again. But with that being said, it looks like that our model, our multi-class classification model has learned something. The loss is going down, the accuracy is going up, but we can further evaluate this by making and evaluating predictions with a PyTorch multi-class model. So how do we make predictions? We've seen this step before, but let's reiterate. Make predictions. We're going to set our model to what mode? Eval mode. And then we're going to turn on what context manager? Inference mode, because we want to make inference. We want to make predictions. Now, what do we make predictions on? or what are the predictions? They're going to be logits, because why? They are the raw outputs of our model. So we'll take model 4, which we just trained, and we'll pass it the test data. Well, it needs to be blob test, by the way. I keep getting that variable mixed up. We just had enough problems with the data, Daniel. We don't need any more. You're completely right. I agree with you. But we're probably going to come across some more problems in the future. Don't you worry about that. So let's view the first 10 predictions. Y logits, what do they look like? All right, just numbers on the page. They're raw logits. Now, how do we go from logits to prediction probabilities? How do we do that? With a multi-class model, we go ypredprobs equals torch.softmax on the y logits. And we want to do it across the first dimension. And what do we have when we go predprobs? Let's go up to the first 10. Are we apples to apples yet? What does our y blob test look like? We're not apples to apples yet, but we're close. So these are prediction probabilities. You'll notice that we get some fairly different values here. And remember, the one closest to 1 here, the value closest to 1, which looks like it's this, the index of the maximum value is going to be our model's predicted class. So this index is index 1. And does it correlate here? Yes, 1. Beautiful. Then we have index 3, which is the maximum value here. 3. Beautiful. And then we have, what do we have here? Index 2. Yes. Okay, wonderful. But let's not step through that. We're programmers. We can do this with code. So now let's go from predprobs to pred labels. So y preds equals, how do we do that? Well, we can do torch.argmax on the y pred probs, and then we can pass dim equals 1. We could also do it this way, y pred probs call dot argmax. There's no real difference between these two, but we're just going to do it this way, call torch.argmax, y preds, let's view the first 10. Are we now comparing apples to apples when we go y blob test? Yes, we are. Have a go at that. Look, 1, 3, 2, 1, 0, 3, 1, 3, 2, 1, 0, 3. Beautiful. Now, we could line these up and look at and compare them all day. I mean, that would be fun, but I know what's something that would be even more fun. Let's get visual. So, plot.figure, and we're going to go fig size equals 12.6, just because the beauty of this being a cooking show is I kind of know what ingredients work from ahead of time, despite what you saw in the last video with all of that troubleshooting. But I'm actually glad that we did that because, seriously, shape issues and data type issues, you're going to come across a lot of them. They're two of the main issues I troubleshoot, aside from device issues. So let's go xblob train and yblob train. And we're going to do another plot here. We're going to get subplot 1, 2, 2. And we're going to do this for the test data. Test, and then plot decision boundary. Plot decision boundary with model 4 on x blob test and y blob test as well. Let's see this. Did we train a multiclass? Oh my goodness, yes we did. Our code worked faster than I can speak. Look at that beautiful looking plot. We've separated our data almost as best as what we could. Like there's some here that are quite inconspicuous. And now, what's the thing about these lines? Would this model have worked? I posed the question a fair few videos ago, whenever we created our multi-class model, that could we separate this data without nonlinear functions? So how about we just test that? Since we've got the code ready, let's go back up. We've got nonlinear functions here. We've got ReLU here. So I'm just going to recreate our model there. So I just took ReLU out. That's all I did, commented it out. This code will still all work. And, or fingers crossed it will. Don't count your chickens before they hatch, Daniel. Come on. We're just going to rerun all of these cells. All the code's going to stay the same. All we did was we took the nonlinearity out of our model. Is it still going to work? Oh my goodness, it still works. Now, why is that? Well, you'll notice that the lines are a lot more straighter here. Did we get different metrics? I'll leave that for you to compare. Maybe these will be a little bit different. I don't think they're too far different. But that is because our data is linearly separable. So we can draw straight lines only to separate our data. However, a lot of the data that you deal with in practice will require linear and non-linear, hence why we spent a lot of time on that, like the circle data that we covered before. And let's look up an image of a pizza. If you were building a food vision model to take photos of food and separate different classes of food, could you do this with just straight lines? Well, you might be able to, but I personally don't think that I could build a model to do such a thing. And in fact, PyTorch makes it so easy to add non-linearities to our model, we might as well have them in so that our model can use it if it needs it, and if it doesn't need it, well, hey, it's going to build a pretty good model, as we saw before, if we included the non-linearities in our model. So we could uncomment these and our model is still going to perform quite well. That is the beauty of neural networks, is that they decide the numbers that should represent our data the best. And so, with that being said, we've evaluated our model, we've trained our multi-class classification model, we've put everything together, we've gone from binary classification to multi-class classification. I think there's just one more thing that we should cover, and that is, let's go here, section number 9, a few more classification metrics. So, as I said before, evaluating a model, let's just put it here, to evaluate our model, our classification models that is, evaluating a model is just as important as training a model. So I'll see you in the next video. Let's cover a few more classification metrics. Welcome back. In the last video, we evaluated our multi-class classification model visually, and we saw that it did pretty darn well because our data turned out to be linearly separable, so our model, even without non-linear functions, could separate the data here. However, as I said before, most of the data that you deal with will require some form of linear and non-linear function. So just keep that in mind, and the beauty of PyTorch is that it allows us to create models with linear and non-linear functions quite flexibly. So let's write down here, if we wanted to further evaluate our classification models, we've seen accuracy. So accuracy is one of the main methods of evaluating classification models. So this is like saying, out of 100 samples, how many does our model get right? And so we've seen our model right now is at testing accuracy of nearly 100%, so it's nearly perfect. But of course, there were a few tough samples, which, I mean, a little bit hard. Some of them are even within the other samples, so you can forgive it a little bit here for not being exactly perfect. What are some other metrics here? Well, we've also got precision, and we've also got recall. Both of these will be pretty important when you have classes with different amounts of values in them, so precision and recall. Accuracy is pretty good to use when you have balanced classes. So this is just text on a page for now. F1 score, which combines precision and recall. There's also a confusion matrix, and there's also a classification report. So I'm going to show you a few code examples of where you can access these, and I'm going to leave it to you as extra curriculum to try each one of these out. So let's go into the keynote. And by the way, you should pat yourself on the back here because we've just gone through all of the PyTorch workflow for a classification problem. Not only just binary classification, we've done multi-class classification as well. So let's not stop there though. Remember, building a model, evaluating a model is just as important as building a model. So we've been through non-linearity. We've seen how we could replicate non-linear functions. We've talked about the Machine Learning Explorer's motto, visualize, visualize, visualize. Machine Learning Practitioner's motto is experiment, experiment, experiment. I think I called that the Machine Learning or Data Scientist motto. Same thing, you know? And steps in modeling with PyTorch, we've seen this in practice, so we don't need to look at these slides. I mean, they'll be available on the GitHub if you want them, but here we are. Some common classification evaluation methods. So we have accuracy. There's the formal formula if you want, but there's also code, which is what we've been focusing on. So we wrote our own accuracy function which replicates this. By the way, TP stands for not toilet paper, it stands for true positive. TN is true negative, false positive, FP, false negative, FN. And so the code, we could do torch metrics. Oh, what's that? But when should you use it? The default metric for classification problems. Note, it is not the best for imbalanced classes. So if you had, for example, 1,000 samples of one class, so number one, label number one, but you had only 10 samples of class 0. So accuracy might not be the best to use for then. For imbalanced data sets, you might want to look into precision and recall. So there's a great article called, I think it's Beyond Accuracy, Precision and Recall, which gives a fantastic overview of, there we go, this is what I'd recommend. There we go, by Will Coeshran. So I'd highly recommend this article as some extra curriculum here. See this article for when to use precision recall. We'll go there. Now, if we look back, there is the formal formula for precision, true positive over true positive plus false positive. So higher precision leads to less false positives. So if false positives are not ideal, you probably want to increase precision. If false negatives are not ideal, you want to increase your recall metric. However, you should be aware that there is such thing as a precision recall trade-off, and you're going to find this in your experimentation. Precision recall trade-off. So that means that generally if you increase precision, you lower recall. And inversely, if you increase precision, you lower recall. So check out that just to be aware of that. But again, you're going to learn this through practice of evaluating your models. If you'd like some code to do precision and recall, you've got torchmetrics.precision or torchmetrics.recall, as well as scikit-learn. So scikit-learn has implementations for many different classification metrics. Torchmetrics is a PyTorch-like library. And then we have F1 score, which combines precision and recall. So it's a good combination if you want something in between these two. And then finally, there's a confusion matrix. I haven't listed here a classification report, but I've listed it up here. And we can see a classification report in scikit-learn. Classification report. Classification report kind of just puts together all of the metrics that we've talked about. And we can go there. But I've been talking a lot about torch metrics. So let's look up torch metrics accuracy. Torch metrics. So this is a library. I don't think it comes with Google Colab at the moment, but you can import torch metrics and you can initialize a metric. So we've built our own accuracy function, but the beauty of using torch metrics is that it uses PyTorch-like code. So we've got metric, preds, and target, and then we can find out what the value of the accuracy is. And if you wanted to implement your own metrics, you could subclass the metric class here, but let's just practice this. So let's check to see if, I'm going to grab this and copy this in here. If you want access to a lot of PyTorch metrics, see torch metrics. So can we import torch metrics? Maybe it's already in Google Colab. No, not here, but that's all right. We'll go pip install torch metrics. So Google Colab has access to torch metrics, and that's going to download from torch metrics. It shouldn't take too long. It's quite a small package, beautiful. And now we're going to go from torch metrics, import accuracy. Wonderful. And let's see how we can use this. So setup metric. So we're going to go torch metric underscore accuracy. We could call it whatever we want really, but we need accuracy here. We're just going to set up the class, and then we're going to calculate the accuracy of our multi-class model by calling it torch metric accuracy, and we're going to pass it ypreds and yblob test. Let's see what happens here. Oh, what did we get wrong? Runtime error. Expected all tensors to be on the same device, but found at least 2 devices. Oh, of course. Now, remember how I said torch metrics implements PyTorch-like code? Well, let's check what device this is on. Oh, it's on the CPU. So, something to be aware of, that if you use torch metrics, you have to make sure your metrics are on the same device by using device-agnostic code as your data. So if we run this, what do we get? Beautiful. We get an accuracy of 99.5%, which is in line with the accuracy function that we coded ourselves. So if you'd like a lot of pre-built metrics functions, Be sure to see either scikit-learn for any of these or Torch metrics for any PyTorch-like metrics, but just be aware, if you use the PyTorch version, they have to be on the same device. And if you'd like to install it, what do we have? Where's the metrics? Module metrics. Do we have classification? There we go. So look how many different types of classification metrics there are from Torch metrics. So I'll leave that for you to explore. The resources for this will be here. This is an extracurriculum article for when to use precision and recall. And another extracurriculum would be to go through the Torch metrics module for 10 minutes and have a look at the different metrics for classification. So with that being said, I think we've covered a fair bit. But I think it's also time for you to practice what you've learned. So let's cover some exercises in the next video. I'll see you there. Welcome back. In the last video, we looked at a few more classification metrics, a little bit of a high-level overview for some more ways to evaluate your classification models. And I linked some extra curriculum here that you might want to look into as well. But we have covered a whole bunch of code together. But now it's time for you to practice some of this stuff on your own. And so, I have some exercises prepared. Now, where do you go for the exercises? Well, remember, on the learnpytorch.io book, for each one of these chapters, there's a section. Now, just have a look at how much we've covered. If I scroll, just keep scrolling, look at that. We've covered all of that in this module. That's a fair bit of stuff. But down the bottom of each one is an exercises section. So all exercises are focusing on practicing the code in the sections above, all of these sections here. We've got number 1, 2, 3, 4, 5, 6, 7. Yeah, 7 exercises, nice, writing plenty of code. And then of course, extra curriculum. So these are some challenges that I've mentioned throughout the entire section 02. But I'm going to link this in here, exercises. But of course, you can just find it on the learnpytorch.io book. So if we come in here and we just create another heading, exercises and extra curriculum. And then we just write in here, see exercises and extra curriculum here. And so if you'd like a template of the exercise code, you can go to the PyTorch Deep Learning repo. And then within the extras folder, we have exercises and solutions. You might be able to guess what's in each of these. Exercises, we have O2 PyTorch classification exercises. This is going to be some skeleton code. And then of course we have the solutions as well. Now this is just one form of solutions, but I'm not going to look at those because I would recommend you looking at the exercises first before you go into the solutions. So we have things like import torch, set up device agnostic code, create a data set, turn data into a data frame, and then etc., etc. for the things that we've done throughout this section. So give that a go, try it on your own, and if you get stuck, you can refer to the notebook that we've coded together, all of this code here. You can refer to the documentation, of course, and then you can refer to, as a last resort, the solutions notebooks. So give that a shot, and congratulations on finishing section 02, PyTorch classification. Now, if you're still there, you're still with me, let's move on to the next section. We're going to cover a few more things of deep learning with PyTorch. I'll see you there.